Hello there and welcome to Science for Sleep, where we take large scientific questions, slow them down, and give ourselves enough time to understand what is actually going on. Tonight we are dealing with something that sounds as though it belongs in a science fiction film. The fastest and most energetic particles moving through our galaxy, the natural machines that produce them, and a new way of finding out where they come from. The title of this story is "We Found the Fastest Thing in the Universe," although there is an important detail to clear up before we go any further. In physics, once a particle with mass is moving extremely close to the speed of light, giving it more energy does not make its speed increase by very much. It simply gets closer and closer to that universal speed limit without reaching it. So when scientists talk about the most extreme cosmic rays, the remarkable thing is not that one of them is dramatically faster than another. The remarkable thing is how much energy has been packed into a single particle, and the numbers become unreasonable very quickly. A particle from space can arrive with an energy of 1,000,000,000,000 electron volts, or a tera electron volt. Some reach 1,000 times higher than that, into the peta-electron volt range. 1 peta-electron volt, usually shortened to 1 PeV, is a quadrillion electron volts. That is a 1 followed by 15 zeros. It is an enormous amount of energy for a single subatomic particle, and nature somehow produces particles like this without a power station, a national budget, or a committee meeting. That alone would be interesting. The real problem is that we have known about extremely energetic cosmic rays for more than a century, and for much of that time we have not been able to point confidently at the objects that accelerated them. They arrive at Earth from space. We detect the showers of secondary particles they create in the atmosphere. We measure their energies. We know that many of the lower energy and intermediate energy cosmic rays around us are probably produced somewhere inside the Milky Way. But if you ask a very simple question, where exactly did that one come from? The answer becomes surprisingly difficult. That is the mystery we're going to work through tonight, before we get into particle accelerators, gamma rays, exploding stars, pulsars, binary systems, and an observatory sitting more than 4 kilometers above sea level. I would like to ask you something simple. Where are you listening from tonight? And if you happen to be near a window, can you see any stars from where you are? You do not need a dark mountain sky. A street lamp, a cloudy evening, or the glow of a city is perfectly acceptable. The reason I ask is that somewhere beyond whatever is outside your window, particles are crossing the galaxy at speeds so close to the speed of light that ordinary human comparisons stop being useful. Some will pass through interstellar magnetic fields for thousands of years. Some will collide with gas or radiation. A small number will eventually contribute to the particle showers that instruments on Earth can detect. If you enjoy these long, quiet scientific journeys, you can leave the video a like and subscribe to the channel. It helps other people find the series, and it reassures the algorithm that spending an evening discussing quadrillion electron volt particles is a perfectly normal bedtime activity. Now we can get comfortable with the basic problem. Cosmic rays have a slightly misleading name. They are not rays in the same sense as visible light. Most cosmic rays are charged particles. Many are protons, which are the positively charged particles found inside atomic nuclei. Others are heavier atomic nuclei, and there are also electrons and other components mixed into the population. They move through space at enormous speeds and can carry energies far beyond anything produced in ordinary thermal processes. The word charged is where our detective story immediately becomes inconvenient. The Milky Way contains magnetic fields. They're not arranged like the neat field around a small bar magnet on a classroom desk. Galactic magnetic fields are spread across enormous distances, with ordered components, turbulent components, and local structures. A charged particle moving through those fields does not simply travel in a perfectly straight line from its source to Earth. Its path bends. That means a cosmic ray can arrive from one direction, even though the object that accelerated it lies somewhere else. Imagine trying to work out where a leaf began its journey after watching it tumble through a windy city for several hours. You can see where it lands. You can inspect the leaf. You might even know roughly how strong the wind has been. But drawing a straight line backward from its final position to the tree it left would be a bad strategy. Cosmic rays give astronomers a much more difficult version of that problem. The higher the particle energy, the less strongly magnetic fields can deflect it, but for the galactic cosmic rays we are interested in, the route can still become scrambled enough to hide the source. That is why simply detecting a very energetic cosmic ray does not automatically reveal the accelerator that launched it. For decades, astronomers had excellent suspects. Supernova remnants were among the most attractive. A massive star explodes, a shock wave expands through surrounding material, charged particles encounter magnetic fields around that shock, and under the right conditions they can gain energy through a process known as diffusive shock acceleration. It is a powerful idea, and supernova remnants clearly can accelerate particles to very high energies. The trouble comes when we ask whether they can account for the most extreme galactic particles, especially those around the famous feature in the cosmic ray spectrum known as the knee. If you plotted the number of cosmic rays against their energy, the distribution would not form one perfectly smooth slope. Around energies of a few peta-electron volts, the slope changes. Astronomers call this feature the knee because the graph bends slightly, and scientists, when given the opportunity to name a complicated astrophysical feature after a body part, rarely resist. LHAASO researchers describe the origin of cosmic rays in this knee region as one of the major unresolved questions in cosmic ray physics. The knee matters because it sits near the upper end of the range where we expect a large contribution from accelerators in our own galaxy. If ordinary galactic sources are responsible for particles reaching those energies, then somewhere in the Milky Way there must be machines capable of accelerating protons into the PeV range. Those hypothetical machines acquired a wonderfully direct name: PeVatrons. A PeVatron is a natural accelerator capable of pushing particles to peta-electron volt energies. The term is deliberately reminiscent of machines such as the PeVatron or the Large Hadron Collider, except the Milky Way version may involve a collapsed star, an expanding shock front, a cluster of massive stars, or a compact object feeding from a companion. Human particle accelerators are built from magnets, vacuum systems, radio frequency cavities, detectors, precision engineering, and a truly heroic quantity of wiring. Cosmic accelerators tend to use gravity, magnetic fields, stellar winds, shocks, rotation, and occasionally an entire dead star. The frustrating part was never whether the galaxy could accelerate particles to high energies at all. We already had plenty of evidence that it could. The difficult part was finding clear evidence of acceleration all the way into the PeV regime, and then identifying the source responsible. This is where gamma rays become extremely useful. Gamma rays are photons, particles of light with much higher energies than visible light. Unlike protons and atomic nuclei, photons carry no electric charge. Magnetic fields therefore do not bend their paths in the same way. A gamma ray travelling across the Milky Way can give astronomers something much closer to a straight line back toward the region that produced it. That makes gamma rays useful as messengers. They're not always simple messengers. A high-energy gamma ray can be produced in more than one way. Very energetic electrons can generate gamma rays through interactions with radiation fields. High-energy protons and atomic nuclei can also produce gamma rays after colliding with surrounding matter. Sorting out which process dominates in a particular source can be difficult, and this distinction matters enormously if your goal is to prove that a source is accelerating hadronic cosmic rays. Still, when gamma rays reach extraordinary energies, they allow us to investigate environments where extraordinary particle acceleration must be occurring. This brings us to LHAASO, the Large High Altitude Air Shower Observatory in China. The name sounds like someone began describing the facility and decided that every useful fact should go directly into the title. Large? Yes, High altitude, very. Air showers, absolutely. Observatory. Fortunately, also, yes. LHAASO sits on Heise Mountain in Daocheng, Sichuan, at an altitude of about 4,410 meters. It was designed to study cosmic rays and gamma rays over a very wide range of energies, with particular strength at the extreme high energy end. Instead of looking through a conventional telescope and collecting light with a mirror, its detector arrays watch what happens when high energy particles and gamma rays strike Earth's atmosphere. A gamma ray with enormous energy does not usually survive all the way down to the ground. It enters the atmosphere and interacts, producing secondary particles. Those particles produce more particles, and a cascade develops. By the time the disturbance reaches the altitude of an observatory, such as LHAASO, it has become an extensive air shower spread over a large area. The original gamma ray is gone, but it has left evidence. With a sufficiently large detector array, scientists can reconstruct important properties of the event. They can estimate the energy of the original particle and infer the direction it came from. They also have to distinguish showers initiated by gamma rays from the much more common showers caused by ordinary cosmic rays, which is a little like trying to hear one particular kind of raindrop during a storm, except the raindrops are subatomic and the useful ones may arrive very rarely. This is one reason scale matters. At these energies, the flux is tiny. You cannot build a detector the size of a dinner plate, leave it outside, and expect a convenient petavolt gamma ray to arrive before breakfast. High-energy astronomy often becomes a problem of collecting area. If nature sends only a small number of particles, the observatory needs to watch a very large patch of ground and keep watching for a long time. LHAASO was built for exactly this sort of work. Its results changed the situation quickly. Early observations revealed multiple sources emitting gamma rays above 100 tera-electron volts, and photons were detected extending into the peta-electron volt range. By 2024, LHAASO's first gamma-ray source catalogue had increased the known population of ultra-high energy sources to 43, according to the observatory's summary of its ultra-high energy program. The message was becoming difficult to ignore. Extreme particle acceleration was not confined to one strange object in one unusual corner of the Milky Way. The galaxy appeared to contain an entire population of powerful accelerators. That was surprising because the traditional picture had been narrower. For years, supernova remnants occupied a central place in explanations of galactic cosmic rays, and for good reason. Supernova explosions release tremendous energy. Their expanding remnants produce strong shocks, and the basic acceleration mechanism is well established. But observations at the very highest energies have made the story less comfortable. As of 2026, LHAASO researchers were still emphasizing that young supernova remnants had not produced the expected detections above 100 teravolts, leaving serious questions about whether they can act as the PeVatrons required by the simplest version of the traditional picture. So the suspect list has grown. Pulsars are on it. These are rapidly rotating neutron stars left behind after certain stellar explosions. A neutron star can pack more mass than the Sun into a sphere roughly the size of a city, rotate rapidly, and support magnetic fields that make anything attached to an ordinary refrigerator look deeply unambitious. Around some pulsars are pulsar wind nebulae, regions filled with energetic particles driven by the rotating compact object. Massive star-forming regions are on the list too. Young, heavy stars produce powerful winds. Groups of them can create enormous bubbles, shocks, and turbulent environments where particles may be repeatedly accelerated. The Cygnus region has become especially important because LHAASO detected a giant ultra-high energy gamma-ray structure there, including multiple photons above 1 peta-electron volt and one reaching about 2.5 peta-electron volts. The collaboration interpreted the observations as evidence for an accelerator capable of driving cosmic ray particles to energies of roughly 20 peta-electron volts. Then there are systems that look almost excessive, even by high-energy astrophysics standards. The Crab Nebula, one of the best-known objects in the high-energy sky, contains a pulsar embedded inside the expanding remains of a supernova. It has served for years as a calibration source because it is bright and comparatively steady at many high energies, yet observations have shown that it can produce gamma rays reaching extraordinary energies, forcing physicists to ask how its particles are being accelerated so efficiently. And then we have objects such as Cygnus X3. Cygnus X3 is an X-ray binary containing a compact object orbiting a massive companion star. Matter, radiation, stellar wind, intense gravity, and relativistic outflows all occupy the same neighbourhood. In results reported by the LHAASO collaboration in late 2025, variable gamma-ray emission from Cygnus X3 extended from about 0.06 to 3.7 peta-electron volts after correcting for absorption, with the observed variability suggesting that the emission originates within or close to the binary system itself. Models considered by the researchers require protons to reach tens of peta-electron volts. That is not what a simple old picture of galactic cosmic ray production would have led us to expect. The Milky Way is beginning to look less like a galaxy with one standard type of cosmic accelerator and more like a place where several very different environments have discovered their own methods for pushing particles toward extreme energies. Some may use supernova shocks, some may use pulsar winds, some may rely on the combined winds and turbulence of many massive stars. Compact binary systems may contribute through jets and intense interactions close to their central objects. The same energy range can therefore become a meeting place for very different pieces of astrophysics. This is why the current search is so interesting. We're not merely trying to find the biggest number on an energy scale. We're trying to understand a physical process that operates in environments we cannot reproduce on Earth. We want to know what combination of magnetic field, shock speed, size, turbulence, radiation, and available time allows a natural source to accelerate a proton from an ordinary energy to 1,000,000 billion electron volts and beyond. There is also a second question hiding inside the first one. Even if we identify a source that produces PeV gamma rays, have we definitely found the source of PeV cosmic rays? Not necessarily. Gamma rays are excellent directional clues, but they can come from energetic electrons as well as from energetic protons and nuclei. A source can look like a PeVatron in gamma rays, while the underlying particle population is still being debated. This is why researchers combine gamma ray observations with measurements at other wavelengths, theoretical models, maps of surrounding gas, and searches for neutrinos. Neutrinos are especially tempting because if very high-energy protons collide with matter and produce certain unstable particles, gamma rays and neutrinos can emerge from the same general chain of interactions. Neutrinos are extremely difficult to detect, but they can provide unusually clean evidence that hadrons, particles such as protons, are involved. Searchers with IceCube have already targeted LHAASO's ultra-high energy sources, although the early searches did not find significant neutrino emission from the initial sample. So even with an observatory as powerful as LHAASO, this is not a case where one detector points at the sky, flashes a green light, and prints the words PeVatron found. Astronomy is rarely so considerate. Instead, a source appears, its gamma-ray spectrum is measured, its shape on the sky is mapped. Astronomers check what known objects lie nearby. They compare the gamma rays with X-rays, radio emission, gas clouds, pulsars, supernova remnants, and star-forming regions. They ask whether electrons can explain the observations. They ask whether protons can explain them better. They calculate how long particles could remain confined, how quickly they lose energy, and whether the source is old enough, large enough, magnetized enough, and energetic enough to do what the data suggest. Then another observation arrives and makes the situation more complicated. That last part is not a flaw. It is usually how progress looks. For a long time, the origin of galactic cosmic rays was often discussed as though the main task were to confirm the correct member of a short suspect list. recent ultra-high energy observations are suggesting something more interesting. There may not be one type of PeVatron. There may be many. Some may dominate at certain energies. Some may accelerate mostly electrons. Others may accelerate protons and heavier nuclei. Some may operate only briefly, meaning we see the particles long after the accelerator itself has faded. Others may remain active for thousands or even millions of years in extended regions. And all of this has been sitting above us while human beings worried about much slower things, such as delayed trains, and whether the microwave has really been running for 3 minutes or only 30 seconds. The particles do not care about our schedules. A proton at PeV energy can cross enormous galactic distances while moving at a speed extremely close to that of light. It carries information about some violent event or powerful environment, but because magnetic fields alter its path, most of that directional information has been scrambled by the time we see it. Gamma rays help restore part of the missing map. They let us identify locations where particles are being driven to energies that once seemed rare or exceptional. LHAASO has made that map much busier. Ultra-high energy gamma ray sources are now known across the Milky Way, and the number itself creates a new problem. If these accelerators are common, why did we miss them for so long? How many different mechanisms are operating? Which sources actually produce the cosmic rays that reach Earth? Are the particles near the knee mainly coming from a few exceptional systems, from a large population of ordinary ones, or from some mixture that changes with energy? The story begins with an instrument that would not stay charged. In the early years of the 20th century, physicists already knew that certain materials were radioactive. Uranium, radium, and other substances could release radiation energetic enough to ionize the surrounding air. An electroscope, which could hold an electrical charge, would gradually lose that charge because the air around it was being ionized. That part made sense. The annoying detail was that electroscopes kept losing their charge even when experimenters tried to shield them from known radioactive materials. Something else was producing ionization. The most obvious explanation was the ground itself. Earth contains naturally radioactive elements, so perhaps radiation coming from the rocks and soil was responsible. If that idea was correct, moving an instrument farther away from the ground should make the radiation weaker. A German physicist named Theodor Wolff tried something close to that in 1909. He carried an electroscope to the Eiffel Tower and measured ionization hundreds of meters above Paris. The radiation did decrease, but not nearly as much as expected if the ground were the only source. It was an interesting result, but not enough to settle the matter. The obvious next step was to go higher. This was slightly more complicated in 1912 than it sounds today. There were no research aircraft waiting on a runway, no pressurized cabins, no satellite instruments, and certainly no convenient button labelled "Measure Mysterious Radiation at 5 kilometers." Scientists used balloons. Victor Hess, an Austrian physicist, began making balloon ascents carrying carefully prepared electroscopes. He wanted to measure how atmospheric ionization changed with altitude. The expectation was simple. If the radiation came mainly from radioactive material in the ground, the signal should steadily decrease as the balloon climbed. At first it did, then it stopped decreasing. Then it began increasing. During his balloon experiments, Hess reached altitudes above 5,000 meters and found that the ionization rate became several times stronger than it was near the surface. He also performed measurements during a near-total solar eclipse. The radiation did not disappear when the moon blocked the sun, which helped rule out the sun as the main direct source of the mysterious penetrating radiation he was measuring. Hess concluded that something was entering Earth's atmosphere from above. It was an extraordinary result, although the scientific community did not immediately respond by closing all the textbooks and declaring the mystery solved. Quite the opposite. Finding the radiation created several new questions. What was it? Where was it coming from? How was it being produced? And how could something from space penetrate so deeply into Earth's atmosphere? Those questions would occupy physicists for decades, and one of them is still with us. Hess had discovered evidence for cosmic radiation, but he had not discovered its sources. Other balloon experiments confirmed that the radiation became stronger at higher altitude. Werner Kohlhörster climbed even higher and found a dramatic increase in ionization. By then, the conclusion was difficult to avoid. Earth was being continuously bombarded by something arriving from outside the atmosphere. Robert Millikan later helped popularize the name cosmic rays. The name stayed. It is also slightly misleading. When most people hear the word ray, they imagine something like a beam of light, an X-ray, or perhaps a dramatic green line emerging from a machine in an old science fiction film. Cosmic rays, however, are mostly not rays of electromagnetic radiation at all. They are particles. Most primary cosmic rays are atomic nuclei. Protons, which are hydrogen nuclei, make up the largest part. Helium nuclei are the next major component, with heavier nuclei contributing as well. Electrons form a much smaller fraction. These particles arrive at Earth carrying a remarkable range of energies, and the most energetic among them exceed the energies produced in human particle accelerators by enormous factors. Learning that cosmic rays were particles took time. During the 1920s and early 1930s, physicists debated whether the incoming radiation consisted mainly of extremely energetic gamma rays or electrically charged particles. If they were charged, Earth's magnetic field should affect their trajectories. Careful measurements eventually demonstrated effects consistent with charged particles, and the picture began to become clearer. Cosmic rays turned out to be useful for another reason as well. Before scientists could build powerful accelerators on Earth, nature was already sending high-energy particles directly to us. When cosmic rays collided with atoms in the atmosphere, they produced particles that physicists had never seen before. The positron, the antimatter partner of the electron, was discovered in cosmic ray tracks by Carl Anderson in 1932. Muons were also identified through cosmic ray studies a few years later. For a period, if you wanted to study particles at energies beyond what laboratory equipment could provide, the sky was effectively supplying the experiment for free. Free is perhaps generous. The universe provided the particles. Physicists still had to build the detectors, climb mountains, launch balloons, spend years studying photographic plates, and persuade funding agencies that staring at invisible things falling from the sky was useful. There was another complication. The particle that reaches a detector at ground level is often not the same particle that originally entered the atmosphere. A high-energy proton approaching Earth may collide with the nucleus of a nitrogen or oxygen atom tens of kilometers above the surface. The collision can produce several new particles. Those particles can collide or decay and produce more particles. The result is a cascade known as an extensive air shower. One cosmic ray can therefore create a spreading swarm of secondary particles. Some of those secondaries reach the ground. If the original cosmic ray has enough energy, the shower can cover a very large area. Instead of catching the original particle directly, scientists place detectors across the ground and reconstruct what happened from the debris. It is a little like trying to determine the properties of a bowling ball by examining the pins after somebody has thrown it through the ceiling. Fortunately, physicists have become extremely good at examining the pins. The direction of the shower tells them something about where the incoming particle was travelling. The number and types of secondary particles help estimate the primary particle's energy and, with considerably more difficulty, its mass. As researchers collected more and more cosmic ray events, one of the most important patterns began to emerge. Cosmic rays are common at relatively modest energies. They become much rarer as the energy increases. If you plot the number of detected cosmic rays against their energy, the result follows something close to a power law over an enormous range. Roughly speaking, every time you move to much higher energies, the number of particles drops dramatically. Below the PeV region, the spectrum is approximately proportional to energy raised to about the power of minus 2.7, although modern measurements reveal additional structure and deviations from one perfectly simple law. The practical consequence is easy to understand. Low-energy cosmic rays arrive frequently. Extremely high-energy ones do not. The universe has no problem producing vast numbers of ordinary cosmic rays. If you insist on studying the truly extreme particles, however, nature becomes rather stingy. At sufficiently high energy, directly carrying a detector into space becomes impractical, because you would need an enormous collection area to catch enough particles. Ground-based air shower observatories become essential. Instead of building one small detector and hoping an extraordinarily rare cosmic ray hits it, researchers monitor huge areas and use Earth's atmosphere as part of the detector. This method opened access to energies that would otherwise be almost impossible to study. And that is where physicists encountered a bend. Around a few peta-electron volts, approximately a few quadrillion electron volts, the cosmic ray energy spectrum becomes noticeably steeper. This feature is called the knee. The name is wonderfully ordinary considering what it represents. Imagine plotting the spectrum as a descending line. At the knee, that line changes slope, as though the graph has bent slightly. The knee was recognized in air shower measurements in the late 1950s, and it quickly became one of the central clues in the search for the origin of galactic cosmic rays. Modern studies commonly place the all-particle knee around a few peta-electron volts, although the detailed picture depends on the different nuclear components being measured. Why should the spectrum bend there? That question turns out to be much harder than naming the bend. One possibility is that the knee tells us something about the accelerators. Perhaps the objects producing most galactic cosmic rays can accelerate particles only up to a certain maximum energy. As that limit is approached, fewer sources are able to contribute and the spectrum steepens. Another possibility is that the knee tells us more about transportation than acceleration. Cosmic rays do not stay in the Milky Way forever. Our galaxy contains magnetic fields that can trap and redirect electrically charged particles. At lower energies, a cosmic ray can bounce through turbulent galactic magnetic fields for a very long time before eventually escaping. As particle energy increases, confinement becomes less effective. If high-energy particles escape the galaxy more readily than lower-energy ones, their observed spectrum could change. The knee might therefore be partly an accelerator problem, partly a propagation problem, or some combination of both. That distinction matters enormously. If the knee represents an acceleration limit, we should be looking for galactic objects capable of pushing particles to PeV energies. If it mainly reflects escape from the Milky Way, then sources might be capable of going higher, while the galaxy simply becomes less effective at keeping those particles around. Researchers have been debating versions of these possibilities since the knee was discovered. There is another clue hidden in the composition. Not every cosmic ray has the same electric charge. A proton has charge number 1, a helium nucleus has charge number 2, iron has charge number 26. Magnetic fields respond to a particle's rigidity, which depends on its momentum relative to its electric charge. Because of this, an accelerator or propagation process controlled by magnetic rigidity may produce energy limits that scale with nuclear charge. In a simplified picture, protons might begin dropping out first. Helium could continue to somewhat higher energies. Heavier nuclei could extend farther still. Instead of one species suddenly stopping at the knee, different components might change one after another, creating the combined spectrum we measure. That is one reason cosmic ray composition around the knee is so important. It is also extremely difficult to measure. At lower energies, a detector carried into space can sometimes identify the primary particle more directly. At PeV energies, researchers usually infer composition from the particle shower produced in the atmosphere. A proton shower and an iron nucleus shower are statistically different, but not in a beautifully neat way where one arrives wearing a label. Atmospheric cascades fluctuate. Different models of particle interactions can produce somewhat different predictions. Researchers therefore collect enormous numbers of events and look for population-level patterns rather than identifying every individual primary cosmic ray with certainty. Even after measuring energy and composition, the largest problem remains: direction. Cosmic rays are charged. The Milky Way is magnetized. Put those two facts together, and the path from source to Earth becomes bent. A photon can usually travel in a straight line across the galaxy. If a telescope detects light from a star, astronomers can point back toward the direction the photon arrived from and see the star. A cosmic ray proton does not offer that courtesy. As it moves through the galactic magnetic field, its trajectory changes. Turbulence adds further deflections. By the time the particle reaches us, the direction from which it enters Earth's atmosphere may tell us very little about where its journey began. This is one of the central reasons the cosmic ray origin problem survived for so long. We could detect the particles, we could measure their energy, we could estimate what they were made of. But the particles themselves had misplaced the return address. The effect becomes weaker as energy increases because more energetic charged particles are harder to deflect. At sufficiently extreme energies, cosmic rays can retain more directional information. Unfortunately, those particles are also much rarer, and at the very highest energies many are believed to come from outside the Milky Way, rather than from galactic sources. The Ni region occupies an especially interesting middle ground, because the particles are energetic enough to probe the limits of galactic accelerators, but still strongly influenced by the galaxy's magnetic environment. So astronomers had to investigate the problem indirectly. They began asking what objects in the Milky Way had enough available energy to maintain the cosmic ray population. A successful source had to satisfy several conditions. It needed large energy supply. It needed a mechanism capable of transferring some of that energy into charged particles. It needed magnetic fields arranged in a way that allowed particles to be accelerated rather than simply carried away. It needed to operate often enough, or for long enough, to explain the cosmic rays filling the galaxy. And if it was responsible for the Ni, it somehow had to accelerate particles toward PeV energies. Supernova remnants quickly became one of the leading candidates. A supernova releases an extraordinary amount of energy when a star explodes. The expanding blast wave moves through surrounding gas and creates a shock. Charged particles interacting repeatedly with shock structures and magnetic turbulence can gain energy through diffusive shock acceleration. The idea is elegant because the energy budget works reasonably well, and because supernovae occur in the Milky Way, often enough to provide a continuing population of remnants. For decades, this became the standard broad picture. Supernova remnants accelerate much of the galactic cosmic ray population, while the particles then diffuse through the Milky Way under the influence of its magnetic fields. There is substantial evidence that supernova remnants really do accelerate high-energy particles. The difficult question is how high? Can they routinely reach the Ni? Can they accelerate protons to several peta-electron volts? Do they do it only briefly when the remnant is very young? If the most powerful phase lasts for only a short period, we might have very few examples available to observe at any particular moment. That makes the search rather unfair. A supernova remnant can survive as a visible object for thousands or tens of thousands of years, while its most extreme particle acceleration might occur during a much shorter interval. We could look at a perfectly respectable remnant today and find no evidence of PeV acceleration, simply because its most energetic period ended long ago. The particles themselves may already have escaped. Once they leave the accelerator, those cosmic rays diffuse through surrounding space. Some may interact with nearby gas clouds and produce secondary radiation far from the original acceleration site. The source and the visible signal do not necessarily occupy the same location. This is the sort of detail that makes astrophysicists very fond of large maps. Meanwhile, alternative suspects remained available. Pulsars possess enormous rotational energy and powerful magnetic fields. Pulsar wind nebulae contain populations of extremely energetic particles. Massive stars produce fast stellar winds. Clusters of young stars can fill large regions with shocks and turbulence. Binary systems containing neutron stars or black holes can generate relativistic jets. The region around the supermassive black hole at the centre of the Milky Way offers another extreme environment. Each candidate had attractive qualities. None immediately solved the entire problem. By the end of the 20th century, the situation had become slightly strange. Humanity had known about cosmic rays since 1912. We understood particle physics vastly better than Hess did. We had built accelerators, satellites, X-ray telescopes, radio observatories, gamma-ray instruments, neutrino detectors, and enormous arrays of particle detectors. We knew that the galaxy was full of high-energy particles. We had good physical mechanisms capable of accelerating them. We had plausible astronomical objects that could provide the necessary power. Yet if someone asked, which objects are producing the cosmic rays around the knee, there was still no simple answer. More than a century after Hess carried his instruments into the sky, papers could still accurately describe the origin of cosmic rays as an unresolved problem. Even recent work continues to frame the search for galactic accelerators around the knee as one of the major open questions in high-energy astrophysics. Part of the reason is that the origin of cosmic rays may have been too broad a question. There may not be one origin. Lower-energy galactic cosmic rays may receive contributions from several populations of sources. Different elements may reach different maximum energies. The dominant accelerator at one energy may not dominate at another. A source capable of accelerating electrons to spectacular energies is not automatically the source of high-energy protons. And the objects that create particles near the knee may represent only a small, unusually powerful subset of the galaxy's accelerator population. This changed the question. Instead of asking which general class of object might accelerate cosmic rays, astronomers increasingly needed to find direct evidence that particular places in the Milky Way were capable of reaching the peta-electron volt range. That is a much stricter test. A source that produces tera-electron volt particles is impressive. A source that reaches hundreds of tera-electron volts is more impressive. But if the knee involves protons at energies of a few peta-electron volts, then the galaxy needs accelerators that can enter an entirely different regime. A PeVatroton carries a quadrillion electron volts. For comparison, its rest energy is less than 1 billion electron volts. The proton is therefore moving so close to the speed of light that adding still more energy barely changes its speed. The extra energy goes overwhelmingly into making the particle harder to stop, harder to bend, and harder to produce in the first place. No material accelerator tube stretches across the Milky Way. No engineer adjusts a control panel. Whatever performs the acceleration has to use naturally occurring magnetic fields, shocks, turbulence, rotation, gravity, or some combination of them, and it has to keep the particle confined long enough to continue accelerating it. That last requirement is important. An accelerator can have enormous energy available and still fail if the particle simply escapes too early. Imagine trying to make a tennis ball faster by repeatedly hitting it with rackets arranged along a corridor. The idea works only if the ball keeps encountering the rackets. If it flies out through an open door after the second hit, your accelerator has become a tennis ball delivery system. Cosmic accelerators face a related problem. A charged particle must remain in the right region long enough to gain energy. Strong magnetic fields can help confine it, while shocks or moving magnetic structures transfer energy to it. As the particle becomes more energetic, confinement becomes increasingly difficult because its trajectory becomes harder to bend. Eventually, either the acceleration process runs out of time, the accelerator runs out of size, the magnetic field becomes insufficient, energy losses intervene, or the particle escapes. Every natural accelerator therefore has limits. The knee seemed to be telling us that somewhere around PV energies, one of those limits was becoming visible on a galactic scale. But the cosmic rays arriving at Earth could not easily show us which source was responsible. So scientists needed another messenger. It had to carry information about extreme particle acceleration. It had to travel through the Milky Way without being redirected by magnetic fields, and ideally it needed to emerge from the same environments where cosmic rays were being pushed toward the knee. That messenger was already known: gamma rays. At sufficiently high energies, gamma rays can be produced when accelerated particles interact with matter or radiation near their sources. Because gamma rays are electrically neutral, galactic magnetic fields do not scramble their directions the way they scramble the paths of cosmic ray nuclei. A gamma ray can therefore do something a PeVaproton usually cannot. It can point back, and once astronomers realize that gamma rays reaching tens, hundreds, and eventually thousands of tera-electron volts could act as signposts of extreme acceleration, the century-old mystery acquired a new type of suspect. Scientists began searching for objects powerful enough to deserve a name that sounds less like an astronomical category, and more like a machine somebody forgot to turn off. They called them PeVatrons. The name PeVatron tells you almost exactly what the object is supposed to do. PeV means peta-electron volt, or 10 to the power of 15 electron volts, and the ending comes from the names we give to particle accelerators. Put the two together and you get a natural machine capable of accelerating particles into the peta-electron volt range. That sounds straightforward until you ask nature to actually build one. A proton at 1 peta-electron volt is carrying roughly 1,000,000 times more kinetic energy than a proton with an energy of 1 giga-electron volt. By the time it reaches the PeV range, it is already moving so close to the speed of light that giving it more energy hardly changes its speed at all. The important change is its momentum. It becomes increasingly difficult to bend, increasingly difficult to keep trapped inside an accelerator, and increasingly difficult to give another useful push before it escapes. That last problem is one of the most important things to understand about PeVatrons. Accelerating a charged particle is not simply a matter of having an energetic object nearby. A supernova can release an extraordinary amount of energy. A pulsar can rotate hundreds of times per second. A black hole can sit beside an accretion flow hot enough to produce X-rays. None of that automatically means a proton will leave the neighbourhood with a quadrillion electron volts. The energy has to be transferred to the particle. It has to happen efficiently. And the particle has to remain in the right place long enough for the process to continue. This is why magnetic fields matter so much. A charged particle moving through a magnetic field follows a curved path. The stronger the field, the more tightly the particle can be confined. At relatively low energies, a proton may spiral around magnetic field lines very effectively. As its energy rises, the radius of that motion grows. Eventually, the particle becomes so energetic that the accelerator has trouble keeping it inside. You can think of the accelerator as a fenced field, and the particle as an increasingly determined horse. At first, the fence keeps it circling comfortably inside. Give the horse enough energy and eventually the fence becomes more of a suggestion. For a natural accelerator to reach PeV energies, it therefore needs a useful combination of size, magnetic field strength, available energy, and time. A tiny region with an extremely strong magnetic field might work. A much larger region with a weaker magnetic field might also work. But if the region is too small and the magnetic field is too weak, the highest energy particles simply leave before they can become PeV particles. This basic idea is closely related to what astrophysicists call the Hillis criterion. It provides a rough way of asking whether an astrophysical environment is large enough and magnetized enough to contain a particle of a particular energy. Passing that test does not prove that an object is a PeVatron. It merely tells you that the object is not immediately disqualified by geometry and magnetic confinement. That distinction is useful because the universe contains many places with impressive numbers attached to them. A neutron star can have a tremendous magnetic field. A supernova remnant can span many light years. A stellar cluster can contain numerous powerful winds. The centre of the Milky Way contains a supermassive black hole and a complicated surrounding environment. A source may look promising on paper, yet still fail to accelerate particles efficiently enough. It may lose energy too quickly. Its magnetic field may have the wrong structure. Its accelerator may operate for too short a time. The particles may escape. or the source may accelerate electrons beautifully while being rather disappointing with protons. A PeVatron has to do more than look intimidating. One of the best-known ways of accelerating cosmic rays begins with a shock wave. Suppose a massive star explodes. Material from the explosion expands outward at thousands of kilometers per second and slams into surrounding gas. A shock forms at the boundary. Magnetic fields around that shock become disturbed and turbulent. Now place a charged particle nearby. The particle can cross the shock, interact with magnetic irregularities, scatter back across it, and then cross again. Each crossing gives the particle a chance to gain energy, because the material on the two sides of the shock is moving relative to one another. The particle does not receive its final energy in one enormous kick. It gains energy through repeated encounters. This is known as diffusive shock acceleration, and it is one of the central mechanisms used to explain how supernova remnants can produce high-energy cosmic rays. The process is sometimes compared with a ball bouncing between approaching surfaces. Each time the ball returns, it receives another boost. The astrophysical version involves charged particles, magnetic turbulence, shock fronts, and fewer irritated neighbours asking why you are bouncing a ball indoors. There is good reason to take the mechanism seriously. Supernova remnants are observed to contain populations of highly energetic particles, and shock acceleration provides a natural way of producing broad power law energy distributions resembling those found in cosmic rays. But PeV energies are where the comfortable version of the story starts becoming difficult. The particle must cross the shock enough times. The shock must remain fast. The magnetic field must scatter the particle effectively. And all of this must happen before the accelerator changes too much or the particle escapes. Young supernova remnants are therefore particularly interesting. Shortly after the explosion, their shock waves can be extremely fast. Under the right conditions, the particles themselves may help amplify magnetic turbulence around the shock, making confinement more effective and allowing the accelerator to reach higher energies. The problem is that this most powerful phase may not last very long. A supernova remnant can remain visible for thousands of years, but its period as a genuine proton PeVatron might occupy only a small fraction of that lifetime. Models in which supernova remnants produce particles at the cosmic ray knee often require strong magnetic field amplification and very efficient acceleration during the remnant's early evolution. Some studies suggest that ordinary remnants may struggle to accelerate protons to the knee at all, with the required energies perhaps reached mainly by unusually powerful and comparatively rare explosions. That changes what astronomers should expect to see. Imagine that a particular kind of machine operates for 10,000 years but reaches its maximum setting for only a few decades or centuries. If you inspect a random example, there is a good chance you will arrive after the interesting part is finished. The accelerator may still be there. The particles it accelerated to the highest energies may not be. Those particles escape first precisely because they are the hardest to confine. A source can therefore stop looking like a PeVatron, while the PV cosmic rays it produced continue travelling through the surrounding region. They may encounter a molecular cloud some distance away. Protons entering that cloud can collide with the nuclei of gas atoms. Those collisions can produce unstable particles, including neutral pions. A neutral pion decays almost immediately into gamma rays. Suddenly, the place that glows in ultra-high energy gamma rays may not be the accelerator itself. It may be a nearby target being illuminated by particles that escaped earlier. This is one reason identifying PeVatrons becomes complicated even after astronomers begin observing the right energies. The accelerator, the cosmic rays, and the gamma ray emission do not always have to occupy exactly the same place. A particularly interesting example is the supernova remnant G106.3 plus 2.7. Observations by the Tibet A S-gamma collaboration found gamma ray emission extending beyond 100 teravolts, with the highest energy emission spatially associated with a nearby molecular cloud region. The observations were consistent with the possibility that extremely energetic protons had escaped from an accelerator and were interacting with surrounding gas, making the system a strong PeVatron candidate. Notice the careful language there. Candidate, not certificate, not solved. That caution appears repeatedly in PeVatron research because gamma rays alone can leave an important ambiguity. Protons are not the only particles capable of producing very energetic gamma rays. Electrons can do it too. An electron accelerated to tremendous energy can collide with a low-energy photon and transfer a large fraction of its energy to that photon. The process is known as inverse Compton scattering. The original photon might have come from the cosmic microwave background, infrared radiation, or starlight. After the interaction, it can emerge as a gamma ray. So if we observe a 100 teravolt gamma ray, we know that something extraordinary has happened. We do not automatically know whether a proton or an electron was responsible. That difference is central to the cosmic ray mystery. A source capable of accelerating electrons to PeV energies can reasonably be called an electron PeVatron. It is still an extraordinary natural accelerator. But if we want to explain the origin of the high-energy cosmic rays made primarily from atomic nuclei, what we really want is evidence for hadronic acceleration, meaning protons or heavier nuclei reaching peta-electronvolt energies. A beautiful ultra-high-energy gamma-ray source can therefore be extremely exciting, and still leave the original question open. The Crab Nebula provides a good demonstration of the problem. At the centre of the Crab Nebula sits the Crab Pulsar, the compact remnant of a stellar explosion observed from Earth in the year 1054. The pulsar rotates about 30 times per second and steadily loses rotational energy. That energy drives a wind dominated by relativistic particles, which fills the surrounding pulsar wind nebula. The Crab has long been one of the brightest and most useful sources in high-energy astronomy. Then observations pushed it into an even more extreme category. LHAASO detected gamma rays from the Crab reaching the PeV range, establishing that particles inside the system are being accelerated to remarkable energies. LHAASO's broader 2021 results included photons reaching approximately 1.4 peta-electron volts among 12 galactic ultra-high-energy gamma-ray sources, and the collaboration noted that the Crab was the one case in that initial sample where the responsible PeVatron could be firmly associated with a known source. But the Crab immediately demonstrates why the word PeVatron does not always mean source of PeV protons. The Crab is exceptionally good at accelerating electrons. Electrons inside the nebula produce synchrotron radiation as they move through its magnetic field, and they can also generate very energetic gamma rays through inverse Compton scattering. So the presence of PV gamma rays establishes extreme particle acceleration, but it does not by itself prove that the Crab is responsible for the hadronic cosmic rays near the knee. The universe has given us the accelerator. It has not necessarily given us the accelerator we were originally looking for. Pulsars make the question even more interesting because of the enormous amount of rotational energy available. A newly born neutron star is an extreme object. Its mass is comparable to or greater than that of the Sun, yet it is compressed into a body roughly the size of a city. If it rotates rapidly and possesses a strong magnetic field, the combination can produce huge electric potentials and powerful outflows. The pulsar gradually slows as lost rotational energy goes somewhere. Part of it can feed a wind of relativistic particles. Where that wind meets the surrounding environment, complicated structures of shocks, magnetic fields, and turbulence can develop. These pulsar wind nebulae are among the most efficient particle accelerators known, and the Crab is no longer alone in demonstrating just how far they may go. In 2026, the LHAASO collaboration reported PV gamma-ray emission associated with the pulsar wind nebula powered by PSRJ 1849-0001. The gamma-ray spectrum extended into the PeV range even though the pulsar's spin-down power is substantially lower than that of the Crab pulsar. The result strengthened the case that extreme acceleration in pulsar-powered systems is not limited to one uniquely favourable object. That is an important shift in the story. A few years ago, finding one PeV gamma-ray source could be treated as an exotic exception. Finding many of them means we have to reconsider how common extreme accelerators may be. LHAASO's first major ultra-high energy results were particularly striking for exactly this reason. The observatory reported more than 530 photons above 100 teravolts from 12 galactic sources, with photons extending as high as 1.4 peta-electron volts. Several of those sources lay near plausible counterparts, including pulsar wind nebulae, supernova remnants, and star-forming regions. But most could not immediately be assigned to one definitive accelerator. That is both exciting and inconvenient. Astronomers wanted PeVatrons. They found a sky containing multiple PeVatron candidates. Then they had to work out what all of them were. Massive star-forming regions offer another way to build an accelerator without relying on one isolated explosion. Massive stars are not quiet objects. They produce strong stellar winds, eject matter, flood their surroundings with radiation, and eventually some of them explode. Put many massive stars together in a young cluster, and the environment can become a complicated network of interacting winds, expanding bubbles, shocks, turbulence, and magnetic fields. Instead of one shock accelerating particles, particles may move through a large region containing many opportunities to gain energy. This changes the scale of the accelerator. A supernova remnant is associated with one explosion. A stellar association or star-forming complex can remain active for much longer, with multiple massive stars contributing energy over an extended period. Some stars explode while others continue producing winds. One generation of shocks can run into material shaped by earlier generations. Cosmic rays can remain inside the larger region and interact with structures spread across many light years. The accelerator may not even have a single obvious center. That makes these systems messy to interpret observationally, but nature is under no obligation to make its particle accelerators look tidy on a telescope image. The galactic center provides yet another possibility. In 2016, the HESS collaboration reported evidence that protons in the central region of the Milky Way had been accelerated to PeV energies. The gamma-ray emission from the surrounding molecular gas showed a hard spectrum and a spatial distribution consistent with cosmic rays spreading outward from a central source. The observations pointed toward a PeVatron operating within the central region, with the supermassive black hole Sagittarius A star considered a plausible source of the required acceleration. That result was important because it showed that the search did not have to end with supernova remnants. A black hole environment could enter the suspect list. Pulsars could enter it. Stellar clusters could enter it. Supernova remnants remained there. Binary systems would become increasingly interesting as observations improved. PeV acceleration was beginning to look less like a special trick belonging to one class of object, and more like an extreme state that several kinds of astrophysical systems might reach under the right conditions. There is still a useful question to ask whenever one of these candidates appears. What actually supplies the energy? With a supernova remnant, the reservoir is largely the kinetic energy of the explosion and expanding material. With a pulsar, it is rotational energy. With a stellar cluster, powerful winds and repeated stellar explosions can contribute. Near a black hole, gravitational energy released by infalling matter can become available. In a compact binary, accretion, stellar winds, orbital interactions, and relativistic jets can create additional possibilities. The source of energy changes from one object to another. The basic challenge does not. Some mechanism has to turn a portion of that energy into a population of charged particles. Then those particles have to be kept around while they are accelerated, and the process must outrun the ways in which they lose energy. Electrons face particularly severe energy losses. A very energetic electron moving through a magnetic field emits synchrotron radiation. It can also lose energy through inverse Compton scattering. The more energetic the electron becomes, the more serious these losses can be. This means an electron detected indirectly at peta-electron volt energies usually tells us that acceleration is occurring very efficiently, and in many cases fairly close to where the radiation is being produced. Protons behave differently. They do not suffer the same rapid radiative losses under ordinary galactic conditions. They can retain their energy for much longer and travel considerable distances before interacting. Useful for the proton, inconvenient for the astronomer. An electron may advertise the location of its accelerator because it cannot travel very far before losing energy. A proton can leave. That makes peta-electron volts protons excellent cosmic travelers and terrible witnesses. There is another subtlety in the word PeVatron itself. The accelerator does not necessarily have to be accelerating PeV particles right now. Suppose a young supernova remnant operated as a PeVatron hundreds of years ago. Its highest energy particles escaped first. Today the shock has slowed and its maximum acceleration energy has dropped. If we examine only the current remnant, we might conclude that it cannot produce PeV particles. Yet a nearby gas cloud could still be glowing, because the previously escaped PeV protons have reached it. The current accelerator and its historical maximum are not always the same thing. Astronomers therefore have to reconstruct the life story of a source. How old is it? How fast was its shock in the past? How strong was its magnetic field? How quickly would particles escape at different energies? Is there surrounding gas they could collide with? How long would it take them to reach that gas? Do the observed gamma rays have the spectrum expected from those interactions? The problem starts sounding less like taking a photograph and more like forensic accounting. You're looking at where the energy is now and trying to work out who moved it there. This is one reason the PeVatron question cannot be solved by finding the source with the highest recorded gamma ray energy and handing it a trophy. The source has to fit physically. Its morphology matters. Its spectrum matters. Its age matters. Its surroundings matter. If the gamma ray emission is concentrated directly around a pulsar, an electron interpretation may look attractive. If the emission overlaps a dense molecular cloud offset from the presumed accelerator, escaped protons may become more plausible. If the gamma ray spectrum continues to very high energies without a clear cutoff, the underlying particle population must extend to still higher energies. That last point is worth slowing down for because the gamma ray usually carries only part of the energy of the parent particle. If a proton produces a gamma ray through hadronic interactions, the original proton generally had considerably more energy than the gamma ray we detect. So a source producing gamma rays at hundreds of TeV may require protons extending into the PeV range. A gamma ray can therefore act as evidence for a particle we never directly see. This is the essential trick that transformed the PeVatron search. The cosmic ray itself may wander through magnetic fields and arrive at Earth from a direction that tells us almost nothing. But if another cosmic ray from the same accelerator collides with matter near the source, the resulting gamma ray can leave that region and travel toward us in a straight line. One particle loses the address, the other brings it with it. And that is why the search for the most extreme particle accelerators in the Milky Way gradually became a search for some of the highest energy light in the universe. Not because the gamma rays are necessarily the cosmic rays we are trying to explain, but because they can reveal what the invisible charged particles were doing before those particles escaped. The next difficulty is learning how to read that signal correctly, because a gamma ray arriving from a PeVatron candidate does not come with a note explaining whether its parent was an electron or a proton, how far it travelled before being produced, or which object in a crowded region supplied the original energy. A high-energy proton can leave an accelerator, cross part of the Milky Way, encounter magnetic fields along the way, and arrive at Earth from a direction that no longer points neatly toward its birthplace. A gamma ray behaves differently. It has no electric charge. Galactic magnetic fields do not redirect it in the same way. So if a gamma ray arrives from a particular position in the sky, astronomers can trace that direction back toward the region where it was produced. This sounds like an ideal solution. Detect the gamma ray, follow the line backward, find the PeVatron. Unfortunately, physics noticed that this was becoming too convenient. The first complication is that gamma rays are not cosmic rays in the sense we have been discussing. They are photons. They may be created because energetic cosmic rays interact with their surroundings, but the gamma ray itself is a secondary messenger. It tells us that something energetic happened in a particular place. Working out exactly what happened requires another layer of detective work. That distinction is important because there are several ways to make an extremely energetic gamma ray. One involves protons. Imagine a proton that has been accelerated to peta-electron volt energy. It escapes from its accelerator and enters a region containing ordinary interstellar gas. Eventually it collides with another proton, perhaps one inside a hydrogen atom. At these energies, the collision does considerably more than make the two protons bounce apart. New particles can be created. Among them are particles called pions. There are charged pions and neutral pions, and the neutral ones are particularly useful for our story because they decay almost immediately into gamma rays. The proton does not turn directly into a gamma ray. Instead, some of its energy goes into producing secondary particles, and part of that energy eventually emerges as high-energy light. If astronomers detect those gamma rays, they may be seeing indirect evidence of the proton population that produced them. The original proton might never reach Earth. It does not need to. Its gamma ray messenger can. This is the hadronic explanation for high-energy gamma ray emission. Hadronic simply means that particles such as protons or atomic nuclei are involved. It is exactly the sort of process astronomers would like to identify when searching for the sources of galactic cosmic rays. There is a useful relationship between the gamma ray energy and the energy of the parent proton. A gamma ray produced in this kind of collision generally receives only a fraction of the original proton's energy. The exact relationship depends on the interaction and on the distribution of particles involved, but as a rough guide, observing gamma rays around 100 teravolts can require parent protons reaching roughly the petavolt range. That is why the 100 teravolt region became so important to PeVatron searchers. If a source produces a hard gamma ray spectrum extending beyond 100 teravolts without an obvious cutoff, it becomes difficult to explain the observation without invoking particles at still higher energies. This is one of the signatures researchers use when searching for PeVatron candidates. Notice what has happened. We began with a cosmic ray whose path had been scrambled by magnetic fields. Instead of trying to follow that cosmic ray home, we looked for a collision near its source. The collision created neutral particles. Those neutral particles produced gamma rays. The gamma rays travel toward Earth without having their direction shuffled by the galactic magnetic field. We have replaced an unreliable witness with one that remembers where it came from. There is still a problem. Electrons can produce gamma rays too, and electrons are extremely good at it. Suppose an electron has been accelerated to a very high energy. Space is filled with low-energy photons. Some come from stars. Some are infrared photons produced by dust. Everywhere in the universe there is also the cosmic microwave background, the leftover radiation from the early universe. A fast electron can collide with one of these photons. The electron transfers energy to it. The originally low-energy photon leaves the interaction with much more energy and may become a gamma ray. This is called inverse Compton scattering. The name sounds slightly backward until you remember ordinary Compton scattering, in which an energetic photon transfers some of its energy to an electron. Inverse Compton scattering runs the useful part of the exchange in the other direction. The electron supplies energy to the photon. It is essentially an astrophysical promotion scheme for light. A humble microwave photon enters, a gamma ray leaves. No proton required. This is called a leptonic process because the important accelerated particle is an electron, which belongs to the particle family known as leptons. Now our gamma ray detective has a difficulty. A 100 teravolt gamma ray arrives from a source. Did a peta-electron volt proton create it through a hadronic collision? Or did a very energetic electron produce it through inverse Compton scattering? Those possibilities lead to very different conclusions. If protons are responsible, we may have found evidence for an accelerator capable of producing the same broad kind of particles that dominate the cosmic rays reaching Earth. If electrons are responsible, we have still discovered a remarkable accelerator, but we have not necessarily solved the cosmic ray knee problem. LHAASO's discovery of more than 530 photons above 100 teravolts from 12 galactic sources demonstrated exactly why this distinction matters. Ultra-high energy gamma radiation is a signature of extreme particle acceleration, but both electron and proton PeVatrons can produce it. Of those first 12 LHAASO sources, the Crab Nebula could be associated firmly with a known accelerator, while the responsible PeVatrons for most of the others were not immediately identified. So astronomers need more than a gamma-ray detection. They need the spectrum, they need the shape of the source. They need information about the gas around it. They need observations at other wavelengths. Sometimes they would very much like a neutrino as well, but we will not ask the universe for everything at once. Start with the spectrum. A gamma-ray spectrum tells astronomers how many photons arrive at different energies. Perhaps a source produces many gamma rays around 1 teravolt, fewer around 10 teravolts, and still fewer around 100 teravolts. That general decrease is expected. What matters is exactly how quickly the number falls and whether the spectrum develops a cutoff. A cutoff can indicate that the particles inside the accelerator have reached their maximum energy. If the gamma-ray spectrum begins declining sharply before reaching the ultra-high energy range, the underlying accelerator may simply not be capable of reaching PV energies. If the spectrum continues without a strong breakthrough tens or hundreds of TeV, the case becomes much more interesting. The spectrum is effectively giving us information about particles we cannot see directly. Astronomers can build models of a proton population, calculate the gamma rays that proton collisions should produce, and compare the result with the data. Then they can do the same for electrons. Whichever model survives is not automatically correct, but bad explanations can begin to disappear. Electron models face a particular challenge at extreme energies. Electrons lose energy efficiently. When an energetic electron travels through a magnetic field, it emits synchrotron radiation. The same electron can also lose energy through inverse Compton interactions with surrounding photon fields. At sufficiently high energies, those losses become severe. A peta-electron volt electron cannot casually wander around the galaxy for millions of years while deciding where to produce a gamma ray. Its useful lifetime can be much shorter. That means PeV electrons often need to be accelerated relatively close to the place where we see their radiation. Protons are less considerate. Under ordinary galactic conditions, they can retain their energy for far longer. They can escape their accelerator, diffuse through surrounding space, and interact with a gas cloud some distance away. This difference creates an observational clue. Imagine a gamma-ray source near a pulsar. The highest energy emission is concentrated very tightly around the pulsar, and X-ray observations reveal a nebula filled with energetic electrons. A leptonic explanation might look quite natural. Now imagine a different source. The gamma rays do not peak directly on the suspected accelerator. Instead, they overlap with a large molecular cloud sitting nearby. That starts to look interesting for protons. Gas matters because hadronic gamma-ray production requires something for the cosmic ray protons to hit. A molecular cloud provides plenty of targets. Astronomers can therefore compare gamma-ray maps with maps of interstellar gas. Radio telescopes can trace molecules such as carbon monoxide, which are used to estimate the distribution of molecular hydrogen. Neutral atomic hydrogen can be mapped as well. If the gamma-ray brightness follows the gas distribution, that can support a hadronic interpretation. This does not automatically prove it. Astronomical regions are crowded and coincidences happen. But morphology, meaning the shape and spatial distribution of the emission, can turn a vague suspicion into a much stronger case. G106.3 plus 2.7 provided a useful example. The Tibet AS Gamma collaboration observed gamma-ray emission extending beyond 100 teravolts and found that the very high energy emission was correlated more closely with a nearby molecular cloud than with the pulsar in the region. That geometry strengthened the interpretation in which highly energetic protons interact with the cloud, making the system a strong proton PeVatron candidate. The word candidate remains important. Scientists are careful here because electrons can sometimes imitate proton signals surprisingly well. You can often adjust the electron spectrum, magnetic field, radiation environment, source age, or diffusion assumptions and produce a model that matches at least part of the gamma-ray data. The trick is to make the same model agree with everything else. Suppose electrons are producing the gamma rays through inverse Compton scattering. Those electrons are also moving through magnetic fields. They should therefore produce synchrotron radiation, often visible at radio or X-ray wavelengths depending on their energies and the magnetic field strength. If your electron model requires an enormous population of ultra-high energy electrons, but X-ray telescopes see almost none of the synchrotron radiation those electrons should generate, the model starts to have a problem. A proton explanation may then become more attractive. The opposite can happen too. A bright X-ray nebula around a pulsar can provide exactly the electron population needed to explain the gamma rays. Then, invoking large numbers of peta-electron volts, protons may be unnecessary. This is why high-energy astronomy becomes multi-wavelength astronomy very quickly. The gamma rays may be the most dramatic part of the evidence, but astronomers also want radio observations, infrared maps, optical data when available, X-rays, measurements of surrounding gas, and information about every plausible accelerator in the region. One instrument gives you the crime scene. The others help you work out who was there. There is an additional clue hidden in how the apparent size of a source changes with energy. Particles do not all travel through their environments in exactly the same way. Higher energy particles can escape or diffuse differently from lower energy ones. Electrons also cool as they move away from their accelerator. Suppose a pulsar has been injecting electrons into the surrounding region for thousands of years. The lower energy electrons can survive longer and travel farther. The highest energy electrons lose energy rapidly and may remain concentrated closer to the pulsar. A gamma-ray nebula could therefore appear smaller at higher energies. That shrinking size can provide information about particle cooling and transport. With escaped protons illuminating surrounding gas, a different energy-dependent pattern might appear. Particles with different energies diffuse at different rates. Depending on the source age and the structure of the surrounding material, the gamma-ray morphology can contain a record of when particles escaped and how they propagated. The sky is no longer simply showing us where the accelerator is. It is showing us what the particles did after leaving it. There is a similar amount of information hidden in a gamma-ray spectrum that extends all the way into the PeV range. Consider what it means to detect one PeV photon. A photon with an energy of 1 peta-electron volt carries 10 to the power of 15 electron volts. Visible light photons are normally measured in individual electron volts. So we are dealing with a photon carrying roughly hundreds of trillions of times more energy than an ordinary visible photon. It is still one photon. If you could somehow ask it about its journey, which physicists unfortunately cannot yet do without upsetting several laboratory safety committees, its energy alone would tell you that its source contained particles operating in an extraordinary regime. LHAASO's first major ultra-high energy survey found photons extending to about 1.4 peta-electron volts, and the discovery of 12 sources above 100 teravolts established that PeV-scale acceleration was not restricted to one isolated object. But high-energy gamma rays have difficulties of their own. They do not always cross space completely untouched. A sufficiently energetic gamma ray can interact with a lower energy photon and produce an electron and a positron. The gamma ray disappears, its energy becomes matter. This process is known as pair production. Whether it matters depends on the gamma ray energy, the distance travelled, and the radiation fields along the way. For distant extragalactic gamma ray sources, absorption by background radiation can become a major limitation. Inside the Milky Way, the distances are much smaller than cosmological distances, but at sufficiently high energies, interactions with galactic radiation fields and the cosmic microwave background can still affect what reaches us. Astronomers therefore have to ask whether the spectrum they observe is the spectrum the source originally emitted. Sometimes the answer is nearly yes. Sometimes corrections matter. The gamma ray may be a better directional messenger than a cosmic ray proton, but even the reliable witness can encounter trouble on the journey. Then it reaches Earth and immediately creates another problem. Earth's atmosphere is very good at protecting us from high-energy radiation. This is excellent news for life. It is less convenient for gamma-ray astronomers. Visible light can pass through much of the atmosphere and reach an ordinary optical telescope. Heavy gamma rays do not arrive at the ground intact. They interact high in the atmosphere and trigger cascades of secondary particles. So even when astronomers finally have a neutral messenger that points back toward its source, they usually cannot catch that original messenger directly at the surface. They have to reconstruct it from the shower it leaves behind. A gamma ray enters the atmosphere. It can produce an electron-positron pair. Those particles emit additional high-energy photons. Those photons produce more electron-positron pairs. The process repeats. By the time the cascade reaches the ground, the original gamma ray is gone, and thousands, millions, or even more secondary particles may be spread across a substantial area, depending on the energy. The direction, energy, timing, and composition of that air shower contain information about the original photon. The atmosphere has effectively converted one inaccessible gamma ray into a large particle display. Unfortunately, cosmic ray protons produce air showers too, and they are far more common. This creates one of the most important practical problems in ultra-high energy gamma ray astronomy. Most of the showers hitting your detector are not the gamma rays you want. They are background cosmic rays. Imagine setting up a microphone to listen for one particular bird in a forest where several million other birds have decided to form a choir. The solution is not to ask the choir to be quieter. You learn to recognize the different sound. Gamma ray-induced showers and hadron-induced showers develop differently. A shower initiated by a proton or atomic nucleus tends to contain more muons and has different patterns of secondary particles because nuclear interactions create pions and other hadrons. A gamma-ray shower is more strongly dominated by its electromagnetic cascade of electrons, positrons, and photons. If an observatory can measure the shower carefully enough, particularly its muon content, it can reject a large fraction of the cosmic ray background. This is enormously important above 100 teravolts. The gamma-ray signal is rare. The hadronic background is constant. A detector that merely records every air shower would spend most of its life collecting cosmic rays and wondering where all the gamma rays went. A good ultra-high energy observatory therefore needs several abilities at once. It needs a large collection area because the highest energy gamma rays are uncommon. It needs to operate for long periods because the next useful photon does not arrive according to anyone's observing schedule. It needs enough directional accuracy to locate the source on the sky. It needs useful energy resolution so astronomers can construct the spectrum. And it needs strong background rejection, so a shower caused by an ordinary cosmic ray is not mistaken for the gamma ray messenger we're trying to follow. Traditional imaging atmospheric Cherenkov telescopes solve part of this problem by looking at the brief flashes of Cherenkov light produced when an air shower passes through the atmosphere. They are extraordinarily sensitive and can reconstruct gamma-ray events with good angular resolution, but they generally observe limited regions of the sky at a time and require suitable nighttime conditions. Extensive air shower arrays take a different approach. Instead of pointing a telescope at one small region, they spread detectors across a large area and wait for showers to arrive. They can watch a broad fraction of the sky and operate with a very high duty cycle. At the highest energies, where photons are rare and showers are large, that becomes a powerful advantage. The early LHAASO results showed what happens when that approach is combined with a detector designed specifically for the ultra-high energy regime. More than 530 photons above 100 teravolts were identified from 12 galactic sources, pushing gamma-ray measurements as high as 1.4 petavolts and revealing a population of extreme accelerators whose nature was still uncertain. Those detections changed the basic problem. For decades, astronomers had been asking whether the Milky Way contained PeVatrons. Now the sky was giving them many places to investigate. Some sat near pulsars, some overlapped supernova remnants, some appeared in complicated star-forming regions. Several had more than one plausible counterpart. The gamma rays had done their first job successfully. They had restored direction to a problem in which charged cosmic rays had lost it. What they had not done was identify every accelerator automatically. That requires enough events to build detailed maps, measure spectra over enormous energy ranges, reject the constant background of ordinary cosmic rays, and watch large sections of the galactic plane for sources that earlier instruments might have missed. To do that at energies where individual photons can carry hundreds of tera-electron volts or more, astronomers needed a detector with an unusually large footprint, an unusually high location, several different detector systems working together, and the patience to let Earth's atmosphere perform the first stage of every measurement. That combination was built. Its name was the Large High Altitude Air Shower Observatory, usually shortened to LHAASO. And almost everything about the facility was designed around one inconvenient fact. The particles astronomers wanted to study were extremely rare. At ordinary optical wavelengths, a telescope can collect enormous numbers of photons from a bright astronomical object. Even a faint star may send enough visible light photons toward Earth that a modest telescope can build an image in seconds or minutes. Ultra-high energy gamma-ray astronomy works under very different conditions. Once you reach energies above 100 tera-electron volts, the number of arriving photons becomes tiny. At PeV energies, a detector may wait a long time for individual events from a particular source. Building a conventional telescope with a mirror slightly larger than the previous one is not enough. You need area, a great deal of area. You also need to observe as much of the time as possible, because a gamma ray carrying hundreds of tera-electron volts does not check the observatory schedule before arriving. That combination of rarity and unpredictability helps explain why LHAASO looks so different from the observatories most people imagine. There is no enormous dome opening toward the night sky. There is no single giant mirror. Instead, the observatory spreads across approximately 1.36 square kilometers on Heizhi Mountain in Daocheng, Sichuan, China, at an elevation of about 4,410 meters above sea level. Its completed detector systems combine thousands of electromagnetic particle detectors, more than 1,000 underground muon detectors, a large water Cherenkov detector array, and wide-field Cherenkov telescopes. Together they allow researchers to examine both cosmic rays and gamma rays across a huge energy range. The altitude is not an incidental detail. When a high-energy gamma ray enters Earth's atmosphere, it begins creating the particle cascade we discussed earlier. The shower grows as it travels downward, reaches a maximum size, and then gradually loses particles as the cascade continues. If you build your observatory too low, much of the shower may already have disappeared by the time it reaches your detectors. LHAASO sits high enough that its instruments are closer to the developing air showers. It's not close by ordinary standards, of course. The original gamma ray still begins its interaction kilometers above the detector, but at 4,410 meters, the observatory receives a much richer sample of the shower than a detector near sea level would. The mountain is therefore part of the instrument. So is the atmosphere. That is a useful way to think about LHAASO. It is not simply a machine sitting beneath the sky. The atmosphere above it performs the first stage of every measurement. A gamma ray arrives. The atmosphere converts it into a shower. LHAASO ASO measures the shower. Researchers reconstruct the gamma ray. It is an unusual telescope because the thing it wants to observe never actually reaches the telescope. To make this work across a wide range of energies, LHAASO does not rely on one detector type. Its largest ground array is called KM2A, short for kilometre square array. KM2A is spread over roughly a square kilometre and contains thousands of surface electromagnetic particle detectors, together with a large network of muon detectors. Early descriptions of the completed design listed more than 5,000 electromagnetic detectors and 1,188 muon detectors. The electromagnetic detectors sample particles arriving at the ground from an air shower. Imagine a PeVatrons gamma ray entering the atmosphere above Sichuan. Its cascade spreads as it descends. By the time the shower reaches LHAASO, secondary particles are striking different parts of the array at slightly different times. One detector records a signal, then another, then dozens or hundreds more, depending on the energy and where the shower lands. The pattern is not random. The relative arrival times tell researchers about the orientation of the shower front. From that, they can reconstruct the direction the original particle came from. The number and distribution of particles provide information about the original energy. The shape of the shower provides additional clues about whether the event began with a gamma ray or a charged cosmic ray. That last job is where the muon detectors become particularly important. Cosmic rays made of protons and atomic nuclei are much more common than gamma rays. If LHAASO simply counted every extensive air shower as a gamma ray event, the resulting sky map would be almost completely overwhelmed by ordinary cosmic rays. The observatory therefore needs a way to reject the background. Showers initiated by hadronic cosmic rays generally produce more muons than showers initiated by gamma rays. Muon detectors allow LHAASO to measure this difference. An event with a large muon component is more likely to have been caused by a proton or atomic nucleus. An event with unusually few muons is more likely to have originated from a gamma ray. It is not a perfect yes or no test for every individual shower. Physics rarely supplies those when you would most appreciate one. Instead, researchers use the combination of shower properties to classify events statistically and remove an enormous amount of cosmic ray background. At the highest energies, this separation becomes one of LHAASO's great strengths. The instrument is not merely waiting for air showers, it is continuously asking what kind of particle created each one. Alongside KM2A is another major system, the Water-Cherenkov Detector Array, or WCDA. The WCDA consists of 3 large water ponds divided into detector cells. The completed system contains thousands of photomultiplier tubes beneath purified water. When charged particles from an air shower move through the water faster than light can travel through that medium, they produce Cherenkov radiation, a brief bluish flash that the photomultipliers detect. The completed WCDA contains 3,120 detector units and 6,240 photosensitive probes, with the water several meters deep. Nothing in that description requires the particle to violate relativity. The particle is not moving faster than light travels in a vacuum. Light slows when it passes through a material such as water. A sufficiently fast charged particle can therefore move through the water faster than light moves through the same water. The result is somewhat similar to a sonic boom. An aircraft moving faster than the speed of sound creates a shock wave in air. A charged particle moving faster than the local speed of light in water creates an electromagnetic version of that effect, Cherenkov light. The flashes are faint and brief, which is why sensitive photomultiplier tubes are used. Each recorded flash helps tell researchers that part of an air shower has crossed a particular detector cell at a particular time. Put thousands of those measurements together and the shower begins to take shape. WCDA is especially useful at lower gamma ray energies than the regime where KM2A is strongest. LHAASO describes the water array as covering gamma ray observations from around 100 giga electron volts into the multi-tera electron volt range, while KM2A becomes exceptionally powerful at higher energies. This overlap allows the observatory to study source spectra over a remarkably broad range rather than seeing only one narrow energy band. That broad coverage matters because an accelerator's spectrum contains much of the evidence needed to understand it. Suppose a source is bright at 1 TeV. Interesting. Suppose its emission continues to 10 TeV. More interesting. Then 50, then 100, then several hundred. Now researchers begin asking what kind of particle population could maintain such a spectrum. If observations from different detector systems can follow the same source across multiple orders of magnitude in energy, astronomers can look for changes in slope, spectral breaks, and cutoffs that might reveal where acceleration becomes inefficient. LHAASO also includes wide field of view Cherenkov telescopes, known as WFCTA. These observe Cherenkov light produced by extensive air showers in the atmosphere and contribute especially to measurements of cosmic ray composition and energy. That makes LHAASO unusual even among high-energy observatories. It is both a gamma-ray observatory and a cosmic ray experiment. Those are closely related jobs, but they are not identical. On one side, the observatory detects showers initiated by charged cosmic rays and studies their spectrum and composition. On the other, it searches within the same enormous flow of events for showers initiated by gamma rays and uses them to identify potential cosmic accelerators. It studies the particles whose origins are hidden and the neutral messengers that may reveal those origins. The design also gives LHAASO a very wide field of view. A conventional imaging atmospheric Cherenkov telescope points toward a selected region of the sky and observes it for a particular period. LHAASO works more like a continuous survey instrument. As Earth rotates, different parts of the sky pass through the observatory's field of view. According to the LHAASO collaboration, the facility can monitor roughly 1/7 of the full sky at any particular moment and scan about 2/3 of the sky during a day. Its combination of broad field of view and high duty cycle makes it particularly effective at finding sources that might otherwise receive little observing time. That is extremely useful when you do not know where the interesting object is going to be. A targeted telescope works beautifully when astronomers already have a strong reason to observe a particular pulsar, supernova remnant, or binary system. A survey instrument can discover that the sky contains something nobody thought to target. This distinction became important almost immediately. LHAASO began collecting useful scientific data before the full observatory was finished. By the end of 2019, part of KM2A was already operating, with thousands of detectors connected to the data acquisition system. The water array reached full operation in early 2021, and the facility's construction phase was completed with the instruments fully operational in July 2021. Then the ultra-high energy sky became crowded. Using only the first 308 days of data from half of KM2A, LHAASO identified 12 ultra-high energy gamma-ray sources at high statistical significance. More than 530 photons above 100 teravolts were associated with those sources. One photon reached approximately 1.4 petavolts. That result was more than a new energy record. It demonstrated that the Milky Way contains multiple regions capable of producing particles at energies where PeV acceleration becomes unavoidable. LHAASO describes the 2021 results as the beginning of observational ultra-high energy gamma-ray astronomy. It is worth thinking about how unlikely this sky would have seemed only a short time earlier. Before sensitive surveys at these energies, PeVatrons were often discussed as rare targets that astronomers hoped to identify. A handful of especially extreme objects seemed likely to dominate the conversation. Instead, LHAASO looked across the galactic sky and found source after source. Some had plausible associations with known pulsars, some were near supernova remnants, Some appeared in star-forming regions. Some had complicated fields containing several possible accelerators. A few did not fit comfortably into any simple category. The problem had changed from where is the galactic PeVatron to something closer to why are there so many places doing this? More observing time made the shift even clearer. LHAASO's first source catalogue, officially published in 2024, contained 90 very high-energy gamma-ray sources. 32 were new very high-energy sources. Most relevant to our story, 43 sources were detected in the ultra-high-energy gamma-ray band. That increased the known number of UHE gamma-ray sources by roughly a factor of 3. 43. Not one mysterious accelerator hiding somewhere near the galactic centre. Not 2 exceptional remnants. 43 ultra-high energy sources in the first catalogue. The catalogue also showed that pulsar wind nebulae are efficient producers of ultra-high energy radiation, reinforcing the idea that rapidly rotating neutron stars and their surrounding particle winds play a much larger role in the highest energy sky than older, simpler pictures of galactic cosmic ray acceleration might have suggested. The number itself requires some caution. An ultra-high energy gamma-ray source is not automatically a confirmed proton PeVatron. Some of those objects may be dominated by electron acceleration. Some may contain several unresolved accelerators. A gamma-ray source can also be extended across the sky, meaning the radiation is coming from a region rather than one point-like object. The catalogues tell astronomers where extreme acceleration is happening. Understanding what kind of acceleration is happening remains a separate task. This is where LHAASO's angular resolution and ability to map extended emission become particularly valuable. Consider a complicated star-forming region. There may be massive stars, a pulsar, a supernova remnant, dense molecular clouds, diffuse gas, perhaps more than one energetic object. If gamma rays appear from that general direction, merely knowing that the region is bright does not solve much. Researchers need to know where within the region the emission is strongest. Does it surround the pulsar? Does it trace a gas cloud? Does it form a shell around a supernova remnant? Does it spread across tens or hundreds of light years? Does the shape change with gamma ray energy? Each possibility points toward a different physical interpretation. The Cygnus region became one of the best examples of what large-scale mapping could reveal. Cygnus is one of the most active star-forming regions in the Milky Way. It contains massive stars, stellar associations, pulsars, supernova remnants, compact binaries, and enormous quantities of interstellar gas. In other words, it contains enough high-energy astrophysics to keep several generations of graduate students occupied. LHAASO observations revealed a giant ultra-high-energy gamma-ray structure associated with the Cygnus star-forming region. The collaboration reported photons above 1 peta-electron volt, including one around 2.5 peta-electron volts, and interpreted the emission as evidence for cosmic ray particles extending to approximately 20 peta-electron volts. The result led researchers to describe the region as containing a super PeVatron, meaning an accelerator capable of reaching well beyond the simple 1 peta-electron volt threshold. That result matters for more than the impressive energy. The emission is extended. We are not necessarily looking at one tiny machine sitting at the centre of a clean circle. Particles may be accelerated within a much larger environment shaped by massive stars, stellar winds, shocks, and turbulence. LHAASO is therefore revealing not only new sources but new possible categories of accelerator. Something similar has happened with compact binaries. These systems contain a neutron star or black hole interacting with a companion star. Matter can flow toward the compact object. Relativistic jets can form. Powerful stellar winds can collide. Magnetic fields, shocks, radiation, and high-speed plasma interact within a relatively small region. For years, these objects were known as energetic X-ray and gamma-ray sources, but their importance to the PeV cosmic ray problem was much less certain. LHAASO has been steadily changing that. By July 2026, the collaboration reported that Cygnus X3 produces variable gamma-ray emission reaching the peta-electron volt range. The variability is especially important because it links the extreme radiation to the compact binary itself rather than to a huge surrounding region that might contain an unrelated accelerator. LHAASO's analysis indicates particles reaching at least tens of peta-electron volts, making Cygnus X3 one of the most extreme galactic accelerator systems yet identified. Variable emission is a useful clue because size and variability are connected. If an astronomical source changes rapidly, the emitting region cannot be arbitrarily large. Different parts of a huge region would not be able to coordinate their changes faster than information can travel across it. So when PeVa gamma-ray emission varies, the timescale places constraints on the physical size of the region producing it. Suddenly, a gamma-ray measurement is telling us not just the energy of the particles, but something about the dimensions of the accelerator. LHAASO has also complicated the older supernova remnant story. Young supernova remnants were historically expected to be some of the best galactic PeVatron candidates because their fast shocks provide a natural acceleration mechanism. Yet by 2026, the LHAASO collaboration noted that young supernova remnants had not produced the expected detections above 100 teravolts, leaving significant questions about whether ordinary young remnants routinely accelerate cosmic rays into the peta-electron volt range. That does not mean supernova remnants are irrelevant. They clearly accelerate particles. The question is whether they usually reach the energies needed for the knee, whether only special examples do so, or whether they become PeVatrons during such a brief early phase that catching one in the act is uncommon. LHAASO is forcing those alternatives to become testable. The observatory can also examine cosmic rays directly. That part of its program matters because the gamma-ray search and the cosmic ray spectrum are two sides of the same problem. If the knee contains structure connected to different particle masses or charges, measurements of composition can reveal what kinds of galactic particles are reaching their limits. If gamma-ray observations identify certain classes of accelerators, theorists can then ask whether those populations can produce the composition and energy spectrum LHAASO measures locally, instead of treating gamma-ray astronomy and cosmic ray physics as separate subjects. The same facility helps connect them. This is one reason LHAASO was built with several detector technologies rather than one. KM2A is exceptionally effective in the ultra-high energy gamma-ray regime. WCDA extends observations toward lower energies and provides continuous wide-field monitoring. The Cherenkov telescopes add information useful for cosmic ray composition. Each instrument sees a different part of the same particle cascade problem. Together, they allow researchers to follow astrophysical processes over ranges of energy that would otherwise require several completely separate observatories. There is another advantage that becomes obvious only after years of operation. LHAASO keeps watching. A source that appears unremarkable during 1 month may brighten later. A binary system may flare. A transient event may occur without warning. A long-lived source may gradually accumulate enough gamma-ray events for researchers to measure its spectrum far beyond the energy range where it was initially discovered. High-energy astronomy benefits enormously from patience. Every additional month increases the exposure. Every additional year improves the chance of catching rare events. For faint, ultra-high energy sources, the sky slowly becomes more detailed simply because the detector remains there. That is why the increase from 12 early UHE sources to 43 catalogued ones is not merely a case of astronomers giving more objects names. It reflects a changing view of the Milky Way. The galaxy is filled with particle accelerators operating at energies that were once considered exceptional. Some may be familiar objects behaving more powerfully than expected. Others may represent acceleration mechanisms that were previously underestimated. And some may force researchers to reconsider which sources are responsible for the cosmic rays that have been arriving at Earth since long before Victor Hess carried an electroscope into a balloon. The irony is that LHAASO does not actually see most of these cosmic accelerators directly. It sees secondary particles hitting plastic detectors. It sees muons passing through buried instruments. It sees tiny flashes of Cherenkov light in enormous pools of purified water. From those signals, computers reconstruct showers. From the showers, researchers reconstruct photons. From the photons, they construct maps. From the maps, they infer accelerators thousands of light years away. A PeV gamma ray may have crossed the Milky Way for thousands of years, disappeared high in Earth's atmosphere in a fraction of a second, and left behind a shower spread across the mountainside. A network of detectors measures that debris. Then the direction is calculated closely enough to point astronomers back toward the source. That chain of inference is what has turned LHAASO into such a powerful tool for the cosmic ray problem. And the more carefully the observatory maps the ultra-high energy sky, the less comfortable the old assumption becomes that one familiar class of objects should explain everything. For decades, the most famous candidate was straightforward. A massive star explodes, a shock wave races outward, particles bounce through magnetic turbulence around that shock and gain energy. The Milky Way experiences enough supernovae to supply a large amount of power. The arithmetic was attractive. If young supernova remnants really are the machines responsible for pushing ordinary galactic cosmic rays toward the knee, somewhere among them we should be able to catch evidence that the shocks are reaching those energies. For a long time, that expectation seemed entirely reasonable. A supernova explosion is one of the most energetic events that regularly occurs in a galaxy. When a massive star reaches the end of its life, or when a white dwarf undergoes a thermonuclear explosion, an enormous amount of energy can be released in a matter of seconds. Much of that energy goes into the expanding material thrown outward from the star. The explosion itself may fade from view relatively quickly. The disturbance it creates does not. For thousands or tens of thousands of years afterward, the expanding debris continues pushing into the gas surrounding the original star. This produces a supernova remnant, an enormous structure of hot plasma, compressed gas, magnetic fields, and shock waves moving through the interstellar medium. For cosmic ray researchers, the shock is the important part. A young supernova shock can move at several thousand kilometers per second. That is nowhere near the speed of light, but it is more than enough to create conditions where charged particles can repeatedly gain energy. The process is the diffusive shock acceleration mechanism we met earlier. A particle crosses the shock front. Magnetic irregularities scatter it. The particle crosses back. It encounters material moving at a different speed. Each round trip provides another opportunity to gain energy. After many crossings, a small number of particles reach very high energies. The beauty of the mechanism is that the particles do not all need to receive the same amount of energy. Instead, the process naturally produces a broad distribution in which lower energy particles are common and higher energy particles become progressively rarer. That looks very much like the power law behavior seen in cosmic rays. The agreement is not perfect in every detail, and the particles still have to travel through the galaxy before we detect them, which changes the spectrum further. But the basic resemblance is one reason diffusive shock acceleration became so important. The energy budget offered another reason. The Milky Way contains a persistent population of cosmic rays. Those particles gradually escape from the galaxy, so if the population has existed for billions of years, something must keep replacing them. Supernovae occur often enough and release enough kinetic energy that converting a modest fraction of their explosion energy into cosmic rays could, in principle, maintain much of the galactic population. That combination was hard to ignore. There was a powerful energy source, there was a known population of objects, there was a plausible acceleration mechanism, and there was enough total power available. For several decades, supernova remnants became the leading explanation for galactic cosmic rays. This is sometimes called the supernova remnant paradigm. It does not claim that every cosmic ray in the universe comes from a supernova remnant. The highest energy cosmic rays are generally thought to require extragalactic sources. The question is whether supernova remnants dominate much of the population produced inside the Milky Way, particularly below the knee. That hypothesis has passed several important tests. One of the strongest came from gamma rays. If supernova remnants accelerate protons, those protons should sometimes collide with surrounding gas. Those collisions produce neutral pions, and the neutral pions decay into gamma rays. The resulting gamma ray spectrum contains a distinctive feature at lower energies sometimes called the pion decay bump. In 2013, the Fermi Large Area Telescope detected this characteristic signature in the supernova remnants C443 and W44. That observation provided direct evidence that protons are indeed being accelerated in supernova remnant environments. That was a major result. Before then, astronomers had already observed gamma rays from many remnants, but electrons can also generate gamma rays. Finding the pion decay signature removed much of that ambiguity in IC443 and W44. Supernova remnants really do accelerate hadrons. The old idea was not simply a convenient theory. Nature was actually doing it. There was only one problem. Proving that a supernova remnant accelerates protons is not the same as proving that it accelerates protons to PeV energies. IC443 and W44 are middle-aged remnants. They provide excellent evidence for proton acceleration, but they do not demonstrate that the particles reach the cosmic ray knee. That became the next test. Researchers turned their attention toward younger remnants, where the shocks are faster and the conditions should be more favourable for extreme acceleration. Cassiopeia A became an obvious target. It is the remains of a stellar explosion that occurred only a few centuries ago, making it one of the youngest known supernova remnants in the Milky Way. Tycho's supernova remnant, produced by the stellar explosion observed in 1572, offered another young system. SN1006 RXJ 1713.7-3946, Vela Jr., and several other remnants were studied extensively at X-ray and gamma-ray wavelengths. Many of them showed unmistakable evidence for extremely energetic particles. Some produced tera-electron-volt gamma rays. Thin X-ray filaments around young remnants suggested strong magnetic fields, and electrons accelerated to very high energies. Everything still looked promising. Then astronomers began asking where the spectrum stopped. That question is crucial. A remnant can accelerate particles impressively and still fail to become a PeVatron. Suppose its proton spectrum reaches tens of TeV. That would be extraordinary by laboratory standards. It would also be insufficient to explain cosmic rays at the knee. Push the maximum energy to 100 teravolts. Still impressive. Still not enough. To explain petavolt cosmic rays, the accelerator must continue working for another order of magnitude or more. This is where theoretical models encounter a difficult problem. As a proton becomes more energetic, its motion through a magnetic field becomes harder to bend. Its gyro radius grows. Confinement becomes more difficult. To keep the particle close enough to the shock for repeated acceleration, the magnetic field around the shock must be sufficiently strong and turbulent. The ordinary interstellar magnetic field is generally not enough to make a typical young supernova remnant an efficient PeVatron. Something has to amplify the field. Fortunately, the accelerated cosmic rays themselves may help. Particles streaming ahead of the shock can generate instabilities in the surrounding plasma. Those instabilities can increase magnetic turbulence, which in turn helps scatter and confine additional particles. The accelerator modifies the environment that allows it to accelerate more efficiently. This kind of feedback can raise the maximum attainable energy substantially. Models incorporating strong magnetic field amplification have shown that supernova remnants can approach PeV energies under favourable circumstances. The difficulty is that reaching the knee appears to require rather extreme conditions, and some calculations find that only unusually energetic and relatively rare core collapse supernovae can push light nuclei such as protons and helium to knee-scale rigidities. There is also a timing problem. A supernova remnant does not remain equally powerful throughout its life. Immediately after the explosion, the ejected material expands rapidly. At first, the mass of this ejector is larger than the amount of interstellar matter swept up by the shock. Eventually, the expanding remnant collects enough surrounding material that its evolution changes. It enters what is known as the Sedov-Taylor phase. The shock continues expanding, but it begins slowing. Later, radiative cooling becomes increasingly important. The remnant continues aging. If the shock's ability to reach PeV energies depends on very high velocity and strong magnetic amplification, then the PeVatron phase may occur very early. Possibly extremely early. That creates an observational trap. Young remnants are already rare because supernova explosions in the Milky Way are not everyday events. If each remnant operates as a PeVatron for only a small fraction of its visible lifetime, the number of active supernova remnant PeVatrons in the galaxy at any given moment could be tiny. Imagine a lighthouse that remains standing for 10,000 years, but switches on its brightest lamp for only the first 100. Arriving in year 5,000 and finding the lamp dark would not prove it had never been bright. We may be examining supernova remnants after their highest energy particles have already escaped. In fact, theory predicts that escape should happen in an energy-dependent way. The highest energy particles are the hardest to confine, so they can leave first. As the shock slows, the maximum particle energy decreases. A remnant that once accelerated peta-electron volt protons might later contain only particles at much lower energies. This means the best evidence for its earlier PeVatron phase may no longer be inside the remnant. It could be sitting several or even dozens of light years away. A cloud of gas near the remnant can act as a target. Escaped cosmic ray protons enter the cloud. They collide with ordinary matter. Neutral pions are produced. Gamma rays follow. The accelerator may have weakened, while its surroundings continue displaying evidence of what it did earlier. This picture makes old or middle-aged remnants interesting again. They may no longer be accelerating particles to PeV energies, but they can be surrounded by the particles they released when they were younger. G106.3 plus 2.7 is one of the most important examples. This remnant lies in a region that also contains the pulsar PSRJ 222 9 plus 6 114 and a molecular cloud. The Tibet-AS Gamma collaboration detected gamma rays from the region extending to and beyond 100 teravolts. More importantly, the emission above 10 teravolts correlated better with the molecular cloud than with the pulsar itself. That spatial relationship favours a model in which very energetic protons interact with the cloud and produce gamma rays through neutral pion decay. That is close to what researchers have been looking for, a supernova remnant. Nearby gas, gamma rays beyond 100 teravolts, a morphology consistent with hadronic interactions. G106.3 plus 2.7 is therefore considered an important PeVatron candidate. Even here, the interpretation requires care. The region contains more than one potential accelerator. The pulsar complicates the picture. Electron models have to be tested. The exact history of particle escape has to be reconstructed, so G106.3 plus 2.7 is strong evidence that supernova remnant environments can be connected with particles approaching peta-electron volt energies, but it has not transformed the entire supernova remnant paradigm into a settled fact. Other remnants have created similar debates. Take R XJ 1713.7-3946. It is one of the brightest supernova remnants in TV gamma rays and has been studied extensively because of its shell-like high-energy emission. The gamma rays clearly tell us that particles are being accelerated. The disagreement has been over which particles dominate the emission. Electrons can produce gamma rays through inverse Compton scattering. Protons can produce them through collisions with surrounding gas. Different studies have emphasized different aspects of the multi-wavelength data, the gas distribution, and the magnetic environment. This is typical of the field. Sometimes the question is not whether acceleration occurs. it is whether the particular radiation we observe comes from the particle population. We need to explain the cosmic ray knee. Cassiopeia presents a different disappointment. It is young. It is energetic. Its shock is clearly accelerating particles. It sounds exactly like the sort of object that should be caught operating near maximum power. Yet its gamma-ray spectrum does not simply continue upward without interruption into the PeV regime. The same general issue appears across several young remnants. We observe TV acceleration. We observe energetic electrons. We observe evidence for hadrons in the supernova remnant population as a whole, but the clean signature expected from a currently active proton PeVatron has remained stubbornly difficult to find. By early 2026, this absence had become important enough that researchers gathered specifically to discuss ultra-high energy gamma rays from supernova remnants and the origin of galactic cosmic rays. The LHAASO collaboration noted that LHAASO had not detected gamma rays above 100 teravolts from young supernova remnants, while their teravolt spectra were often steeper than expected for straightforward PeVatron models. That statement lands awkwardly beside the old textbook expectation. If young supernova remnants are the principal accelerators of galactic cosmic rays all the way to the knee, why are the obvious young remnants not shining brightly above 100 teravolts? There are several possible answers. The first is that the PeVatron phase is too short. Perhaps by the time a supernova remnant becomes easy to identify and study, its PV particles have already escaped. A second possibility is that only a minority of supernovae ever reach PeV energies. The most powerful core collapse explosions may be capable of it, while ordinary remnants stop lower. If that is true, the phrase supernova remnants accelerate galactic cosmic rays remains broadly correct, but the knee could be produced by a rare subclass rather than by every typical remnant. Models have found that common remnants can struggle to reach knee energies, while rare, energetic explosions offer more favourable conditions. A third possibility is environmental. A supernova exploding into a dense wind produced by its progenitor star experiences very different conditions from one exploding into a low-density region. The magnetic field differs, the density differs, the shock evolution differs, the amount of surrounding target material differs. A massive star can alter its surroundings for millions of years before it explodes, carving cavities and filling them with stellar wind. When the supernova finally occurs, the shock is not expanding into a generic piece of the interstellar medium. It is entering a structure created by the star's own life. This can change the maximum particle energy dramatically. The environment may therefore decide whether a remnant becomes a PeVatron. Another possibility is that the supernova remnant picture is correct only up to some energy below the knee. Perhaps ordinary remnants produce a large fraction of galactic cosmic rays at giga-electronvolt and teravolt energies, but another population takes over at hundreds of teravolts and above. That would explain why the supernova remnant paradigm works well in some observations, but becomes less convincing at the extreme end. The cosmic ray spectrum does not require one source class to dominate everywhere. Nature is allowed to use several. There is also the possibility that we are asking too much from the term supernova remnant. A massive star does not exist in isolation before it explodes. Many massive stars are born in groups. They spend their lives producing powerful winds. Those winds interact. Earlier stars in the group may already have exploded. The surrounding region may contain old shocks, young shocks, hot bubbles, dense clouds, turbulence, and magnetic structures extending across tens or hundreds of light years. Then another supernova occurs inside that environment. If particles reach peta-electron-volt energies, which object deserves the credit? The individual remnant, the stellar cluster, the combined winds, several supernova shocks acting over time, the entire superbubble. The neat picture of one spherical remnant accelerating one population of cosmic rays may sometimes be too simple. This is part of what LHAASO is beginning to expose. Its ultra-high energy sky contains sources associated with pulsars, stellar associations, molecular clouds, and large extended regions. The first LHAASO detections above 100 teravolts already showed that PeV-scale acceleration was occurring in multiple environments, not simply in a clean sample of young supernova shells. That does not remove supernova from the story. Quite the opposite. A supernova may still supply energy to many of those complicated regions. Its shock may contribute to a larger accelerator. Its escaped particles may illuminate surrounding clouds. The neutron star left behind by the explosion may become another accelerator entirely. A stellar cluster can experience repeated supernovae over millions of years. The problem is no longer deciding whether supernovae matter. They clearly do. The problem is identifying exactly which stage of a stellar explosion produces which part of the cosmic ray spectrum. This is why evidence from IC 443 and W44 remains so important. Those remnants tell us that supernova remnant shocks can accelerate protons. G106.3 plus 2.7 tells us that at least some supernova remnant environments may be connected with protons approaching the peta-electron volt regime. The absence of strong ultra-high energy gamma-ray detections from many young remnants tells us that the simplest version of the theory is incomplete. All three facts can be true at the same time. That is where the subject becomes more interesting than a simple victory or defeat for the old model. Suppose typical remnants accelerate protons efficiently to tens of TeV. Suppose a smaller number reach hundreds of TeV. Suppose only rare explosions operating in unusually favourable environments reach several peta-electron volts. Then the cosmic ray spectrum we measure at Earth could be the combined result of all those populations. Add heavier nuclei, and the picture becomes richer still. A proton with charge 1 and an iron nucleus with charge 26 respond differently to the same magnetic accelerator. If the maximum achievable energy scales roughly with charge, an accelerator that stops protons at a certain energy may push iron nuclei considerably higher. The Ni in the all-particle spectrum could therefore represent several overlapping cutoffs, rather than one universal limit. Protons begin fading. Helium follows at another energy. Heavier nuclei continue farther. The overall spectrum bends gradually. That would mean a supernova remnant does not necessarily need to push every particle species to the same peta-electron volt energy to contribute to the structure around the Ni. Composition measurements are trying to determine whether something like this is happening. But once again, the particles do not point back. The only way to connect a particular bend in the cosmic ray spectrum with a particular class of astronomical source is to combine several forms of evidence. Gamma rays show where extreme acceleration is occurring. Cosmic ray measurements tell us what particles arrive at Earth. Radio and X-ray observations reveal shocks and energetic electrons. Gas maps show where escaped protons might interact. Neutrinos, if detected from the same source, could provide particularly valuable evidence for hadronic processes. The supernova remnant hypothesis has therefore evolved from a simple statement into a collection of testable questions. Do supernova remnants accelerate protons? Yes. We have direct observational evidence that at least some do. Do they accelerate particles into the multi-tera electron volt range? Clearly. Do at least some supernova remnant environments approach peta-electron volt energies? The evidence says that they can, with G106.3 plus 2.7 among the strongest examples. Do ordinary young remnants routinely accelerate protons to the Ni? That is where the answer remains uncertain, and LHAASO's lack of detections above 100 teravolts from young remnants has made the uncertainty hard to ignore. Can supernova remnants alone explain the entire galactic cosmic ray spectrum below the Ni? There is no longer a good reason to assume that the answer must be yes. The old favourite suspects are still in the investigation. They have not been cleared. They have also lost their exclusive claim to the case. That change happened because the ultra-high energy sky began revealing accelerators in places where a clean supernova shock was not the obvious explanation. It may be the compact object that survived the explosion, or the crowded stellar environment in which the star was born. That possibility changes the search considerably, because a supernova explosion is only one stage in the life of a massive star. Before the explosion, the star may spend millions of years blowing material into space. Afterward, it can leave behind a neutron star that continues releasing energy long after the expanding supernova shock has slowed. In some cases, that neutron star becomes a pulsar. A pulsar is one of those astronomical objects whose basic description already sounds excessive. Start with a star more massive than the Sun, allow its core to collapse, compress roughly a star's worth of matter into an object only a few tens of kilometers across, give it a powerful magnetic field, then make the entire object rotate several, dozens, or even hundreds of times per second. You now have something that could reasonably be described as a poor choice for a nearby neighbour. Pulsars are rotating neutron stars with strong magnetic fields. Their magnetic axes are generally not perfectly aligned with their rotation axes, so beams of radiation can sweep through space as the neutron star spins. If one of those beams crosses Earth, radio telescopes or other instruments may detect regular pulses, which is where the name comes from. The pulses made these objects famous. For high-energy astrophysics, however, the important part is not simply that pulsars blink, it is that they rotate. A rapidly spinning neutron star stores an enormous amount of rotational energy. As the pulsar loses energy, its rotation gradually slows. That lost rotational energy can be carried away through electromagnetic radiation and through a wind of relativistic particles, dominated in many models by electrons and positrons. When that wind collides with the surrounding environment, it can produce a pulsar wind nebula, or PWN. The word wind is slightly gentle for what is happening. A terrestrial wind involves air moving past you quickly enough to make an umbrella inconvenient. A pulsar wind can involve charged particles moving at speeds extremely close to the speed of light. Near the pulsar, the wind can remain relatively cold in the technical sense that the particles move together in an organized bulk flow, rather than possessing a broad random distribution of energies. Farther out, that wind eventually encounters surrounding material and slows sharply at what is called the termination shock. A large amount of organized motion now has to go somewhere. Some of it becomes random particle energy. Particles can be accelerated. Magnetic fields become important. Radiation is produced across a huge range of wavelengths. The result can be a bright nebula surrounding a star that is only the size of a city. For many years, pulsar wind nebulae were already known to be excellent electron accelerators. That part was not especially controversial. The real surprise has been just how far those electrons can be pushed. To produce gamma rays in the hundreds of tera-electron-volt or peta-electron-volt range through inverse Compton scattering, electrons themselves may have to reach energies approaching or exceeding a peta-electron-volt. That is difficult. Electrons at these energies lose energy rapidly through synchrotron radiation and inverse Compton scattering. The accelerator therefore has to supply energy fast enough to compete with losses that become increasingly severe as the electrons become more energetic. It is not enough to build a powerful accelerator. You have to build a powerful accelerator while the particle is constantly spending its winnings. The Crab Nebula became the most famous demonstration that pulsar-powered systems can manage this. LHAASO detected gamma rays from the Crab reaching the PeV range, establishing that the nebula contains an extreme particle accelerator. The Crab is powered by a pulsar rotating roughly 30 times per second, and its relativistic wind supplies the surrounding nebula with energetic electrons and positrons. For a while, it was reasonable to wonder whether the Crab was simply exceptional. It is young. Its pulsar is unusually powerful. It is one of the brightest, persistent, high-energy sources in the sky. Perhaps the Crab had won a particularly favourable combination of age, magnetic field, rotational power, and surrounding environment. Then LHAASO began finding evidence that the Milky Way contains other pulsar-powered systems capable of operating in the same extreme regime. Its first gamma-ray catalogue already pointed in that direction. The catalogue contained 43 ultra-high-energy gamma-ray sources, and LHAASO reported that pulsar wind nebulae appear to be highly efficient producers of ultra-high-energy emission. A substantial fraction of the UHE sky was turning out to be associated with energetic pulsars, or systems that could plausibly be powered by them. That matters, because pulsars have one useful property that an expanding supernova shock gradually loses. They can keep supplying energy. A supernova remnant's shock slows as it expands. A pulsar also loses power as it spins down, so it certainly does not have an unlimited supply. But a young energetic pulsar can continuously inject particles into its surroundings over thousands of years. This creates an accelerator with a different history. Instead of one blast wave moving outward and becoming progressively weaker, you have a compact central engine continuously feeding a particle wind. Those particles can accumulate, they can cool, they can escape, they can diffuse into surrounding space, and depending on the age and motion of the pulsar, the resulting gamma-ray source can become much larger than the visible nebula close to the neutron star. That brings us to gamma-ray halos. As pulsars age, particles accelerated earlier in their lives can spread far beyond the compact pulsar wind nebula. Those electrons and positrons interact with background radiation and produce gamma rays over regions extending many light-years from the pulsar. The accelerator may therefore be tiny compared with the area illuminated by its particles. A neutron star only tens of kilometers across can influence a gamma-ray region that would take light-years to cross. Astronomers can use that extended emission to study how particles propagate through the interstellar medium. If the particles spread rapidly, the halo should become broad and diffuse. If diffusion is suppressed around the pulsar, the particles remain concentrated for longer. Either way, the gamma rays allow researchers to examine particle transport around an accelerator whose actual working region is far too small and distant to resolve directly. LHAASO has also found evidence that pulsars do not all create the same kind of surrounding structure. PSRJ 1740100 is a middle-aged pulsar roughly 4,500 light-years from Earth. It is moving through its environment fast enough to produce a bow-shock pulsar wind nebula, a structure somewhat like the wake produced behind a moving object. In X-rays, that system has a comet-like tail. LHAASO used more than 1,200 days of data to detect ultra-high-energy gamma radiation from a position lying along the extension of that tail about 16 light-years from the pulsar. Photons exceeded 300 teravolts, implying that particles in or around the tail may be reaching petavolt energies. The interpretation proposed by the collaboration involves particle reacceleration in the tail rather than a simple, large, symmetric halo. That is a useful warning against expecting every accelerator to resemble the crab. A pulsar can be young or old. It can remain inside its original supernova remnant or escape from it. It can move slowly through surrounding gas or race through it supersonically. Its wind can form a roughly bubble-like nebula, an extended halo, a compressed structure, or a bow shock with a tail. The acceleration conditions change accordingly. The more examples astronomers observe, the less likely it becomes that one neat diagram will describe all pulsar-powered PeV acceleration. Then, in April 2026, LHAASO reported a result that made the problem even more interesting. The source is associated with PSRJ 184-9-0001. Compared with the crab pulsar, this neutron star is much less powerful in terms of its present spin-down luminosity. Its rotational energy loss rate is about 50 times smaller than that of the crab pulsar. You would therefore expect its nebula to be a considerably less impressive accelerator. That would be a sensible expectation. It is also apparently not what nature decided to do. LHAASO detected a point-like ultra-high energy gamma-ray source associated with the Pulsar Wind Nebula around PSR J1849-0001. The measured gamma-ray spectrum extends to about 2 peta-electron-volts, and its luminosity in the peta-electron-volt range is several times greater than that of the Crab Nebula, despite the central pulsar having far less spin-down power. The collaboration nicknamed the system the Aquila Booster. That is a surprisingly cheerful name for an object causing problems for particle acceleration theory. Multi-wavelength observations, including X-ray data, were used to constrain the nebula's magnetic field and particle population. In the researchers' analysis, accelerating electrons to the required energies demands an efficiency approaching the theoretical limits of conventional pulsar wind models. Under a standard termination shock interpretation, the required acceleration can even exceed what ideal magnetohydrodynamic assumptions appear to allow, suggesting that processes such as magnetic reconnection may need to play an important role. In simpler terms, the accelerator appears to be working better than the basic version of the theory says it comfortably should. That is scientifically useful. A theory is most informative when observations push it into a region where its assumptions become visible. If every pulsar wind nebula behaved exactly as the simplest model predicted, researchers would have little reason to investigate additional plasma physics. Instead, LHAASO has found a system with a much weaker central engine than the Crab yet remarkably strong peta-electron-volt gamma-ray emission. Now physicists have to explain how the energy transfer becomes so efficient. Perhaps the acceleration region is not located exactly where traditional models place it. Perhaps the magnetic field geometry matters. Perhaps magnetic reconnection converts stored magnetic energy into particle energy more effectively than standard shock acceleration alone. Perhaps the structure contains more than one acceleration zone. The observation does not select one answer automatically, but it establishes an awkward requirement that any successful model has to meet. And there is another consequence. If a pulsar 50 times less powerful than the Crab can power such an extreme gamma-ray source, then PeVa electron acceleration may not require the most exceptional pulsar in the galaxy. That makes the large number of pulsar-associated ultra-high energy LHAASO sources easier to understand. It also makes the Milky Way a much more active particle acceleration environment than researchers once assumed. There is still an important limitation. Pulsar wind nebulae are spectacular electron accelerators, but the cosmic ray mystery that brought us here is mainly about protons and atomic nuclei. A PeVa electron accelerator does not automatically explain the proton knee. If the ultra-high energy gamma rays from a pulsar wind nebula are produced through inverse Compton scattering, then the observation may tell us little about whether that system contributes significantly to the hadronic cosmic rays reaching Earth. Some pulsar models do allow ions to be accelerated. The question is how many to what energies, and whether they escape into the galaxy in sufficient numbers to matter. That remains much harder to establish observationally. So pulsars solve one problem while leaving another in place. They prove that nature can create extraordinarily efficient compact accelerators. They may contribute to the galactic cosmic ray population, but they do not yet provide a simple replacement for supernova remnants as the source of all cosmic rays around the knee. This is where massive star-forming regions enter the discussion. At first glance, a stellar nursery sounds like a much calmer place than a neutron star. The name suggests gas clouds quietly producing new stars. That is accurate only if you ignore what massive young stars actually do once they appear. An O-type star can be many times more massive than the Sun, enormously luminous, extremely hot, and capable of driving a powerful stellar wind at thousands of kilometers per second. Put one such star in a molecular cloud, and it begins changing its environment. Put dozens or hundreds of massive stars together, and the entire region becomes energetic on a scale difficult to reproduce with one isolated object. The winds collide with surrounding gas. Winds from neighbouring stars collide with one another. Shock waves form. Hot cavities grow. magnetic fields become turbulent. Some of the most massive stars live only a few million years before exploding as supernovae, adding further shocks and additional energy to a region already disturbed by stellar winds. A young massive cluster can therefore operate less like one accelerator and more like an accelerator complex. That difference may help solve one of the difficulties we encountered with isolated supernova remnants. A single remnant has a limited period during which its shock is fast enough to accelerate the most energetic particles. A star-forming region can receive fresh energy for millions of years. One star contributes a wind. Another contributes a wind. A third explodes. The resulting shock passes through material already shaped by previous winds and explosions. Another supernova follows later. Particles may experience repeated acceleration or re-acceleration rather than relying on one shock crossing history. The region has time, it has size, it has turbulence, and it can contain strong local magnetic structures. Those are all useful ingredients if your goal is to prevent an energetic particle from escaping before you've pushed it into the peta-electron volt range. Astronomers had already begun taking massive star clusters seriously as cosmic ray accelerators before LHAASO. Extended gamma-ray emission around regions such as Westerlund. One provided evidence that young clusters could maintain large populations of energetic particles. HESS observations around Westerlund 1 found gamma-ray emission spread across a region roughly 2 degrees wide, with emission extending to tens of TeV. The morphology and spectrum made the massive cluster itself one of the strongest candidates for supplying the required particle population, although the exact acceleration sites and mechanisms remained uncertain. Cygnus then pushed the idea into an entirely different energy range. The Cygnus X region lies in the direction of one of the Milky Way's most active nearby star-forming complexes. It contains large quantities of gas, numerous massive stars, pulsars, supernova remnants, compact binaries, and the enormous association known as Cygnus OB2. Cygnus OB2 contains many young O and B-type stars. Those stars produce powerful radiation and fast stellar winds. Taken together, they can inject a tremendous amount of mechanical energy into the surrounding environment for long periods. Earlier gamma-ray observations had already revealed extended high-energy emission in this general area, often referred to as the Cygnus cocoon. LHAASO then mapped the region at much higher energies and found something far larger and more extreme. The collaboration detected an ultra-high energy gamma-ray bubble covering at least about 100 square degrees of sky. Several photons exceeded 1 peta-electron volt, with the highest reaching approximately 2.5 peta-electron volts. The observed gamma-ray distribution was correlated with surrounding interstellar gas, supporting an interpretation in which high-energy protons interact with that material and produce gamma rays. This is exactly the type of evidence cosmic ray researchers wanted. Not just PeV gamma rays, not just a compact electron accelerator, a huge region in which the gamma-ray morphology can be explained by cosmic ray particles spreading outward and colliding with gas. The LHAASO analysis found that the underlying accelerator must be capable of pushing cosmic ray particles to around 20 peta-electron volts. That is well above the energy of the ordinary proton knee. For that reason, the collaboration described the accelerator as a super PeVatron. The most promising candidate near the center of the bubble is Cygnus OB2. That does not necessarily mean one particular star inside the association is responsible. The attraction of the star cluster explanation is precisely that the accelerator may be collective. Stellar winds can collide, a cluster wind can form, shocks can appear throughout the region, supernova explosions can add further disturbances, large-scale turbulence can scatter particles repeatedly. Instead of searching for one small engine, researchers may be dealing with an acceleration volume extending across a substantial piece of the star-forming complex. The LHAASO morphology supports continuous injection of energetic protons into the surrounding region as one plausible explanation. In that picture, particles are supplied near the central part of the bubble and then propagate outward. Where they encounter dense gas, hadronic collisions generate gamma rays. The gas becomes a kind of screen on which the otherwise invisible cosmic ray population can be mapped. This allows astronomers to study something that direct cosmic ray measurements at Earth cannot show. They can estimate how the particle density changes with distance from the presumed source. They can compare the gamma ray brightness with molecular clouds. They can ask how quickly particles are diffusing. They can test whether one continuous accelerator can account for the size and spectrum of the bubble, or whether several sources are required. Current models are still debating the details. A 2026 transport study of the Cygnus bubble found that reproducing both its spectrum and morphology with hadrons, accelerated in a steady non-relativistic cluster wind source, requires strongly suppressed diffusion and demanding physical conditions, illustrating that even a convincing star-forming region association does not make the acceleration mechanism simple. That uncertainty is useful to keep in mind. Cygnus contains a super PeVatron, and we know exactly how Cygnus accelerates particles to 20 peta-electron volts are not the same statement. The first has strong observational support from LHAASO's gamma-ray measurements. The second is still being worked out. Cygnus OB2 is the leading candidate, but the central region is crowded. The LHAASO bubble contains other energetic objects, including pulsars and the unusual compact binary Cygnus X3. The original LHAASO analysis itself noted that the core region contains Cygnus OB2, Cygnus X3, and previously identified multi-teri electron volt sources. So once again, nature has produced a PeVatron candidate in the least convenient possible neighbourhood. Astronomers can see that something in the region is accelerating particles to extraordinary energies. They can see evidence that those particles are interacting with gas. They can identify a massive stellar association with more than enough activity to be taken seriously. But there are several other powerful objects nearby. Separating their contributions requires better maps, longer observations, spectral measurements at different locations, and comparisons across multiple wavelengths. The ambiguity also reveals something important about the Milky Way. Pulsars and star-forming regions are not unrelated competitors. They are parts of the same stellar life cycle. A massive star forms inside a stellar nursery. For millions of years, it supplies radiation and wind energy to that environment. Then it explodes. The explosion produces a supernova remnant. If the collapsed core survives as a neutron star, a pulsar may appear. The pulsar can then power a new accelerator inside the region, where its parent star was born and died. One piece of the galaxy can therefore host several generations of particle acceleration. A stellar cluster operates before the explosion. The supernova shock operates afterward. The pulsar can continue long after the brightest supernova phase has faded. Cosmic rays produced during each stage can overlap in space and time. That makes the old question, which object accelerates the cosmic rays, much harder than it first appeared. The answer may occasionally be all of them, at different times and energies. LHAASO's growing sample is making that possibility increasingly difficult to dismiss. Its first catalogue showed that pulsar wind nebulae are efficient ultra-high energy emitters, while the Cygnus observations established a massive star-forming region as the location of a super PeVatron capable of reaching well above 1 PeVatron. The Milky Way may therefore contain several different routes to the same extreme energy range. One route begins with a neutron star only a few tens of kilometers wide. Another involves a stellar association spread across many light years. The first draws energy from rotation. The second draws on stellar winds, shocks, turbulence, and repeated explosions. Both can produce gamma rays above 100 teravolts. Both can enter the petavolt regime. and both are forcing physicists to reconsider how common extreme acceleration really is. Yet there is one object that remains particularly useful because it gives researchers an unusually detailed laboratory for testing these ideas. It has been observed in radio waves, visible light, X-rays and gamma rays, and when LHAASO pushed measurements into the PeV range, this familiar object turned out to be capable of accelerating particles far closer to fundamental physical limits than many models had expected. That object is the Crab Nebula. It is useful to begin with something unusual about the Crab. We know approximately when the object was created because people were watching the sky when the explosion happened. In the year 1054, astronomers in China recorded the appearance of a new guest star. It became bright enough to be visible during the daytime for a period and remained noticeable in the night sky for many months. We now know that those observers were witnessing a supernova in our part of the Milky Way. The expanding debris from that explosion became the Crab Nebula, located roughly 6,500 light-years from Earth. That historical record gives astronomers something they rarely receive from an astrophysical object, a reasonably well-known birthday. The nebula is only about 1,000 years old. At its centre is the object left behind when the original star's core collapsed, a neutron star known as the Crab pulsar. It rotates roughly 30 times each second and steadily loses rotational energy. That lost energy powers a relativistic wind dominated by electrons and positrons, which in turn supplies the surrounding nebula with energetic particles. The Crab is therefore a classic pulsar wind nebula, and decades of observations have made it one of the best-studied particle accelerators in astronomy. If you could somehow stand beside the neutron star, which would be a very short experiment for several reasons, you would encounter conditions that have no useful everyday comparison. The pulsar is only tens of kilometers across, its magnetic field is enormous, its surface is rotating rapidly. Charged particles and electromagnetic fields interact in a region where a huge amount of rotational energy is being converted into an outward relativistic flow. That wind eventually encounters the surrounding nebula. The transition cannot continue smoothly forever. At some distance from the pulsar, the wind is forced to slow at a termination shock, where its bulk energy can be converted into disordered particle motion and radiation. This is one of the leading places where researchers think extreme particle acceleration occurs. The Crab has therefore functioned almost like a laboratory for pulsar physics. Not a laboratory where scientists can turn knobs, unfortunately. More the kind where the equipment is 6,500 light-years away, was built by a supernova, and refuses to provide a manual. Still, astronomers have an extraordinary amount of information to work with. The Crab emits radiation across a huge range of wavelengths. Radio telescopes detect low-energy synchrotron emission. Optical telescopes reveal the famous filamentary nebula. X-ray instruments see energetic structures close to the pulsar. Gamma-ray observatories measure particles operating at much higher energies. Before LHAASO reached the PeV regime, observations had already established the general picture. Relativistic electrons and positrons inside the nebula produce synchrotron radiation while moving through magnetic fields, and those same particles can produce very high-energy gamma rays by inverse Compton scattering of surrounding low-energy photons. That two-part radiation mechanism is extremely useful. Synchrotron emission tells researchers about the relationship between the particles and the magnetic field. Inverse Compton emission tells them about energetic electrons interacting with radiation fields. Measure both carefully enough, and the same electron population can be examined from two different directions. The Crab became so reliable at high energies that astronomers began using it as a standard candle. That does not mean its brightness is absolutely constant at every wavelength or on every timescale. The Crab has surprised astronomers with flaring behaviour in some gamma-ray bands. But over the energy ranges useful for many ground-based measurements, it has long served as one of the standard sources against which instruments can check their performance. LHAASO itself used the Crab to calibrate measurements in the ultra-high energy regime. This makes what happened next particularly helpful scientifically. If you are opening a new observational window, you want to look at something you already understand well. Then, if the object suddenly stops behaving as expected, you have a much better chance of figuring out whether the surprising part is the source or the instrument. LHAASO measured the Crab's gamma-ray spectrum across roughly 3.5 orders of magnitude in energy, extending its observations into territory beyond 100 teravolts and all the way to about 1.1 peta-electron volts. And there, the Crab became uncomfortable again. Among the recorded events was a gamma-ray carrying approximately 1.1 peta-electron volts of energy. Remember what that means. 1 photon, 1 particle of light, more than a quadrillion electron volts. This was not simply another point added to a familiar spectrum. If the standard electron interpretation of the Crab's gamma-ray emission was correct, then an electron inside the nebula had to be even more energetic than the gamma-ray that eventually reached Earth. The LHAASO analysis connected the 1.1 peta-electron volt photon with a parent electron carrying about 2.3 peta-electron volts. That is where the scale becomes difficult to appreciate. Humanity has built extremely powerful particle accelerators. The Large Electron-Positron Collider, which once occupied the tunnel later used by the Large Hadron Collider at CERN, accelerated electrons and positrons to energies of roughly 100 billion electron volts per particle. The electron inferred inside the Crab carried more than 2 quadrillion electron volts. LHAASO described that as around 20,000 times the maximum electron energy reached by LEP. Nature had constructed a dramatically more powerful electron accelerator using a collapsed star and some surrounding plasma. There is an important reason this is more difficult than simply giving a proton the same energy. Electrons radiate strongly. An electron moving through a magnetic field follows a curved trajectory. Whenever a charged particle accelerates, including when its direction changes, it can emit electromagnetic radiation. For relativistic electrons in magnetic fields, this becomes synchrotron radiation. The more energetic the electron becomes, the more severe those energy losses can become. At peta-electron volt energies, an electron cannot simply remain inside a strong magnetic field indefinitely while waiting for occasional boosts. It is constantly losing energy. The accelerator therefore has to compete directly against radiation losses. Imagine filling a bucket that has a hole in the bottom. At first, pouring water in slowly may be enough. Make the hole larger, and the pouring has to become faster. Eventually there is a point where you cannot increase the water level unless you can pour almost as quickly as the bucket is draining. PeV electron acceleration inside the Crab has a similar problem, although the bucket is a relativistic plasma and the leaking water is electromagnetic radiation. That competition between acceleration and cooling creates a natural limit. The electron gains energy from electric or electromagnetic processes in the accelerator. It loses energy through radiation. If the losses become as fast as the gains, pushing the particle farther becomes extremely difficult. This is why LHAASO's Crab measurement attracted so much attention. The required acceleration rate was not merely high. In the collaboration's analysis, it exceeded about 15% of the theoretical maximum acceleration rate allowed under the assumptions used for classical electrodynamics and ideal magnetohydrodynamics. Later, LHAASO summaries commonly describe the figure as roughly 16%. 16% might not sound impressive. If someone tells you that their phone battery is at 16%, you do not normally congratulate the battery. Here the denominator is the important part. The comparison is not with an average astrophysical accelerator, it is with a theoretical upper limit. The Crab appears to be operating within an unexpectedly small distance of the fastest acceleration that the standard physical framework permits. LHAASO estimated that the acceleration efficiency required for these peta-electron volts electrons is around 1,000 times greater than the corresponding efficiency associated with ordinary supernova blast wave acceleration. That makes the crab useful for more than proving that PeVatrons exist. It tests how acceleration itself works. The standard pulsar wind picture begins with energy flowing outward from the pulsar. Before the termination shock, much of that energy may be carried by electromagnetic fields and the organised motion of the wind. At or near the shock, some of it has to become the random energy of individual particles. The difficulty is explaining how a small fraction of those particles reach several peta-electron volts quickly enough. Simple shock acceleration is not automatically sufficient. Researchers have considered magnetic reconnection, turbulent acceleration, shock drift processes, and combinations of mechanisms operating in different parts of the nebula. The observation does not tell us which mechanism wins. It tells us what the winning mechanism must accomplish. That is often how astrophysics narrows a problem. We cannot watch an individual electron as it crosses the acceleration region. We can measure the gamma ray it eventually produces. Then we work backward. The energy of the gamma ray constrains the electron energy. The electron energy, together with the magnetic field, constrains how tightly the particle can be confined. Cooling constrains how quickly the acceleration must occur. The observed spectrum constrains how many particles occupy different energies. Suddenly, one gamma ray is connected to a long list of physical requirements. The magnetic field is especially important. Using the crab's synchrotron emission together with its inverse Compton gamma ray emission, the LHAASO analysis estimated a characteristic magnetic field of roughly 110 microgauss in the relevant nebula region. That may sound tiny compared with the magnetic field near the surface of the neutron star. It is. But the acceleration region being discussed is much farther from the pulsar, inside the surrounding nebula. Even there, the field is strong enough to make PeVatrons losses significant. The same magnetic field also helps confine the particles, and this produces another balancing act. Increase the magnetic field, and particles can be bent more tightly. That is useful for keeping them inside the accelerator. Increase it too much, however, and synchrotron losses become stronger. Now the particle radiates its energy away more quickly. The accelerator has to find conditions in which confinement works without cooling winning too soon. The crab appears to do exactly that. LHAASO's modelling constrained the characteristic size of the heavy acceleration region to roughly 0.025 to 0.1 parsecs under the termination shock interpretation. In astronomical terms, that is compact. In human terms, it is still enormous. A tenth of a parsec is thousands of astronomical units across. Pluto orbits the Sun at tens of astronomical units, so when astrophysicists describe an acceleration region as small, it is worth remembering that they have developed a slightly different sense of scale. The significant point is its size compared with the Crab Nebula itself. The whole nebula extends across several light-years. The most extreme electrons apparently have to be produced within a much smaller central region. That fits what we know about electron cooling. At PeV energies, electrons cannot travel casually across the entire nebula while retaining all their energy. The highest energy particles have to be generated close enough to the central engine that they can radiate before cooling drags them into a lower energy population. The gamma ray data therefore start narrowing the location of the accelerator. The crab pulsar supplies the energy. The pulsar wind transports it. The inner nebula converts some of it into PeV particles. Those particles scatter background photons upward to gamma ray energies. LHAASO detects the resulting air showers on Earth. There is another useful detail above about 100 teravolts. Inside the crab, several photon populations can act as targets for inverse Compton scattering. There is starlight, infrared radiation, synchrotron radiation from the nebula itself, and the cosmic microwave background. At the highest energies measured by LHAASO, the cosmic microwave background becomes especially useful because its properties are very well known. The original crab analysis used this relationship to connect ultra-high energy gamma rays more directly with their parent electrons. That is one reason researchers could estimate approximately 2.3 peta-electron volts for the electron responsible for a 1.1 peta-electron volt photon. At these energies, inverse Compton scattering also enters what is called the Klein-Nishina regime. At lower energies, electrons can transfer energy to photons relatively efficiently. As the interaction becomes more extreme, the physics changes and the scattering efficiency becomes suppressed. The electron does not simply continue producing increasingly energetic gamma rays with the same ease, so PeV gamma ray production is fighting two problems at once. The electrons are losing energy rapidly, and the inverse Compton process itself is entering a regime where producing the highest energy photons becomes less efficient. The fact that the crab does it anyway is precisely why it is such a demanding accelerator. The power budget provides another way of seeing this. According to the LHAASO analysis, the rate at which energy must be supplied to PeV electrons is about 2.5 times 10 to the 36th ergs per second. That represents only about 0.5% of the crab pulsar's total spin-down power. 0.5% sounds modest. Energetically, the pulsar can afford it. The challenge is not the total bank balance. The challenge is transferring that energy into a very small population of particles quickly enough to produce electrons at several peta-electron volts before losses remove the energy. This distinction appears frequently in astrophysical acceleration. An object can possess more than enough total energy and still be incapable of creating the highest energy particles. Having the money is different from being able to spend it quickly in exactly the right place. The crab appears to have both. That raises another question. If the crab is such a good electron accelerator, could it also accelerate protons? Possibly. The standard model of the crab's broadband radiation is dominated by electrons and positrons, and the PeV gamma ray measurements can be explained through leptonic processes. However, the original LHAASO analysis did not rule out a contribution from PeV protons at the highest gamma ray energies. This matters for the larger cosmic ray problem. If pulsar winds contain a meaningful population of energetic ions, then pulsar wind nebulae might contribute not only to high-energy electrons, but also to the proton and nuclear cosmic rays we have been trying to trace. Researchers have explored models in which relativistic protons inside the crab contribute to the hardest end of the gamma ray spectrum, and may eventually escape from pulsar wind nebulae into the galaxy. Such models remain uncertain, and the current gamma ray data do not require a dominant proton component. The safer conclusion is narrower. The crab is unquestionably an extreme electron accelerator. Whether it is also an important source of PeV hadronic cosmic rays remains much less certain. This is a useful reminder that the term PeVatron is describing an energy capability, not automatically identifying the particle species we care about. A proton PeVatron helps solve the traditional galactic cosmic ray mystery. An electron PeVatron reveals equally remarkable acceleration physics, but may contribute to a different part of the high-energy particle population. The crab has done something else important for LHAASO. It provided confidence that PeV gamma ray measurements were real. The crab was already well characterized at lower energies. LHAASO measured its spectrum from roughly 0.5 TeV to 1.1 PeV and found agreement with earlier observations where the energy ranges overlapped. That consistency allowed the crab to function as a calibration source in a region where there had previously been very little observational information. Then the observatory could look elsewhere. When another source produced photons above 100 teravolts, researchers had a well-tested reference. When spectra extended toward a peta-electron volt, the crab provided a comparison. When unidentified LHAASO sources appeared near pulsars, astronomers had a known example showing that pulsar wind nebulae really could reach this regime. In that sense, the crab became both an astrophysical object and a measuring stick. The surprising part is that it may no longer be the most extreme pulsar-powered accelerator LHAASO has found. For years, the crab seemed like an obvious upper benchmark. Its pulsar has one of the highest spin-down powers among galactic pulsars. It is young. Its nebula is bright. If you wanted a neutron star capable of pushing electrons toward the physical limit, the crab looked almost deliberately constructed for the job. That expectation was challenged in 2026 when LHAASO reported PeVy gamma rays from the pulsar wind nebula associated with PSRJ 1849-0001. That pulsar has a spin-down power roughly 50 times lower than the Crab pulsar, yet the surrounding source emits several times more gamma-ray luminosity in the PV range. LHAASO found that the acceleration efficiency in that system reaches at least about 27% of the theoretical upper limit, exceeding the already extreme Crab benchmark. This tells us something slightly uncomfortable. The Crab was not demonstrating the maximum performance of pulsar wind nebulae. It was demonstrating that our previous expectations were too conservative. If a much less powerful pulsar can produce even more efficient PV acceleration, then the details of the acceleration mechanism matter at least as much as the raw power of the central engine. Magnetic geometry may matter, the location of the acceleration region may matter, reconnection may matter, the age of the nebula may matter, the surrounding radiation and magnetic fields may matter. Simply ranking pulsars by spin-down luminosity will not tell us which ones become the strongest petavolt gamma ray sources. This helps explain why LHAASO has found so many ultra-high energy sources associated with pulsars. The Crab is no longer an isolated oddity. It appears to belong to a wider population of pulsar-powered accelerators that can push electrons into the peta-electron volt range. LHAAS. Ultra-High Energy Survey has found numerous sources linked to energetic pulsars, making pulsar wind nebulae one of the most prominent classes in the emerging PV gamma-ray sky. There is, however, an important difference between the Crab and some of the other systems now appearing in the data. The Crab is relatively clean. We know the central pulsar, we know the nebula, we know the historical supernova. We have decades of multi-wavelength observations. The object has been mapped and modelled repeatedly. When a PeV gamma ray arrives from the Crab, astronomers have a detailed physical framework in which to place it. Other sources are not nearly so cooperative. Some lie in crowded regions with several possible accelerators. Some are extended across large areas. Some contain compact binaries with relativistic jets. Some vary with time. Some combine stellar winds, accretion, radiation fields, and shocks in a region small enough that conditions can change rapidly. Those systems can offer something the Crab generally does not: variability. If an ultra-high energy gamma-ray source changes brightness on a measurable timescale, that change places a limit on the size of the emitting region. A very large region cannot brighten everywhere at once faster than information can travel across it. So a variable PV source can help astronomers locate the accelerator much more tightly. That becomes particularly useful in binary systems. A neutron star or black hole can orbit a massive companion. Gas from the companion can feed the compact object. Jets can emerge. The companion's stellar wind provides dense material. Its intense radiation field fills the system with target photons. Particles accelerated near the compact object then encounter matter and radiation almost immediately. The environment is extremely compact compared with a supernova remnant or star-forming bubble. It is also changing constantly as the two objects orbit. For a long time, systems like this were not the first places astronomers looked when trying to explain PeV cosmic rays. The Crab was already forcing researchers to accept that compact objects can accelerate particles much closer to fundamental limits than expected. The next step was to discover whether a compact binary could do something even more surprising. In the direction of Cygnus, roughly 24,000 light-years away, one such system has spent decades producing X-rays, radio outbursts, and high-energy gamma rays, and LHAASO has now detected gamma rays from it extending into the PeV range. The system is Cygnus X3, and compared with the Crab Nebula, it immediately gives astronomers a much less tidy laboratory. The Crab has one young pulsar sitting inside one well-studied nebula. Cygnus X3 contains two stars locked in an extremely tight binary system, although calling one of them a star requires a small qualification. One member is a Wolf-Rayet star, an evolved massive star losing material through an exceptionally powerful stellar wind. The other is a compact object, either a neutron star or a black hole. Despite decades of study, its exact identity is still not completely settled. The two objects orbit one another every 4.8 hours. That means an entire orbit takes less time than many people spend sleeping. During those few hours, the compact object moves through an environment filled with dense stellar wind, intense radiation, hot plasma, magnetic fields, and material being transferred and accelerated around the system. Cygnus X3 also produces relativistic jets, and is therefore classified as a microquasar. The name comes from the resemblance to quasars, where supermassive black holes launch enormous jets from the centres of distant galaxies. A microquasar uses a stellar mass compact object instead, allowing broadly similar accretion and jet physics to operate on a much smaller scale. Smaller does not mean gentle. Cygnus X3 has been known for decades as one of the strangest X-ray binaries in the Milky Way. It can undergo powerful radio outbursts, shift between different X-ray states, and produce giga-electron-volt gamma-ray flares associated with changes in its accretion flow and jet. Very long baseline radio observations have directly revealed relativistic jets during its active states. More recent X-ray polarization measurements have strengthened the picture of a highly energetic, obscured central source channeling a substantial amount of accretion power into an outflow. So even before PeV gamma rays entered the story, Cygnus X3 already had an impressive resume. Then LHAASO found that it could do something much more extreme. The observatory detected variable ultra-high energy gamma rays from the direction of Cygnus X3, with the intrinsic spectrum extending from about 0.06 peta-electron volts to 3.7 peta-electron volts, after correcting for absorption during the photon's journey through the galaxy. The overall signal reached roughly 9.6 sigma in the complete dataset, making the association statistically strong. Two individual photons were reconstructed at about 3.73 and 3.08 peta-electron volts. At the time of the reported analysis, these were the highest energy photons detected from an identified astrophysical source. This deserves some perspective. The Crab photon we discussed earlier carried roughly 1 peta-electron volt. Cygnus X3 produced photons several times more energetic. But the most important part of the discovery was not simply the larger number, it was the timing. Most ultra-high energy gamma-ray sources discovered by LHAASO do not visibly turn on and off over short periods. A supernova remnant may remain detectable for thousands of years. A large stellar association may continuously inject particles into its environment. A pulsar wind nebula can evolve, but it does not usually transform dramatically between 1 month and the next. Cygnus X3 did. When researchers divided the LHAASO observations according to high and low giga-electron-volt gamma-ray states, measured by the Fermi Large Area Telescope, the peta-electron-volt signal changed with them. During the giga-electron-volt high states, the significance of the peta-electron-volt detection increased to about 11.5 sigma. During the low states, it dropped below 2 sigma. The difference between those states provided an 8.6 sigma detection of variability. That was a major clue. If the PeV gamma rays were being generated in a giant cloud, dozens or hundreds of light years from the binary, the emission should not respond quickly when the central system changes. A large cloud does not know immediately that the jet near the compact object has become active. Particles need time to travel. Interactions need time to occur. A large extended region smooths rapid variability away. But the PeV emission from Cygnus X3 followed its active states. The accelerator therefore appeared to be closely connected to the binary itself. Then LHAASO found an even more restrictive hint. The ultra-high energy gamma rays showed evidence of the same 4.8-hour periodicity associated with the orbital motion of Cygnus X3. The statistical significance of this orbital modulation was about 3.2 sigma, so the paper treated it as evidence rather than an absolutely conclusive detection. Combined with the much stronger month-scale variability, however, the pattern strongly favours an origin within or very close to the binary system. This is where Cygnus X3 becomes radically different from the giant Cygnus bubble we met earlier. The bubble extends across an enormous region around the Cygnus star-forming complex. Cygnus X3 is an accelerator squeezed into a system whose characteristic binary scale is only around 3 × 10⁻11 centimeters. LHAASO's interpretation places the relevant acceleration and interaction regions near the innermost part of the relativistic jet. The observatory's public summary described the orbital information as localizing the accelerator to a region roughly a few times the size of the Sun. A machine only a few solar dimensions across may therefore be accelerating particles to tens of peta-electron volts. That is an extraordinary amount of work being performed in a very small place. And small accelerators face the confinement problem we discussed earlier. A PeVa particle does not like being trapped. As its energy rises, its gyroradius increases. To hold it inside a compact region, you need a sufficiently strong magnetic field. The Hillis argument becomes particularly demanding in Cygnus X3 because the available space is so limited. For a characteristic region around 3 × 10⁻11 centimeters, the LHAASO analysis shows that PeV particles require magnetic fields of at least several to tens of Gauss, depending on the particle energy and jet speed. Strong fields help with confinement. For electrons, they create another problem: synchrotron radiation. An ultra-relativistic electron moving through a strong magnetic field loses energy very rapidly. As you try to increase the magnetic field to keep the electron inside the accelerator, you also increase the rate at which the electron radiates away the energy you're attempting to give it. Eventually, there is no useful solution. LHAASO's analysis combined the confinement requirement with synchrotron cooling and found that realistic electrons in the compact Cygnus X3 region cannot reach anywhere near the energies necessary to generate the observed PeV gamma rays. The calculated upper limit is only around 0.07 PeV under the assumptions examined, far below what would be required. The researchers therefore argue that a leptonic explanation for the PeV emission is effectively excluded. That is a major difference from the Crab. In the Crab Nebula, PeV electrons are a convincing explanation for the gamma ray emission. In Cygnus X3, the compact environment makes PeV electrons extremely difficult to maintain. Something heavier is required: protons. Protons do not suffer synchrotron losses nearly as severely as electrons because they are much more massive. They can be accelerated in strong magnetic fields without immediately radiating most of their energy away. That makes Cygnus X3 especially important to our original cosmic ray question. This is not merely an accelerator producing spectacular peta-electron volt gamma rays through electrons. The LHAASO interpretation requires hadrons reaching tens of peta-electron volts. The official 2026 announcement describes particle energies of at least about 30 peta-electron volts. 30 peta-electron volts, 30 quadrillion electron volts, carried by an individual cosmic ray particle. That reaches comfortably beyond the ordinary proton knee. So if the interpretation is correct, Cygnus X3 is not just a PeVatron, it is a super PeVatron. The remaining question is how a proton inside this tiny binary system produces the gamma ray we eventually detect on Earth. One attractive mechanism uses something Cygnus X3 possesses in abundance: light. The Wolf-Rayet companion produces an intense field of energetic photons. The region near the compact object and its accretion flow is also filled with radiation. A proton accelerated in the inner jet can reach sufficient energy to interact with those photons. At extreme energies, the proton-photon collision can produce pions. This is called a photomeson interaction. Neutral pions decay into gamma rays. Charged pions can decay through pathways that eventually produce neutrinos. The source therefore contains all the necessary ingredients very close together. A relativistic jet provides an acceleration environment. Strong magnetic fields help confine the protons. The Wolf-Rayet star supplies an intense photon field. The accelerated proton encounters one of those photons. Pions are produced. Gamma rays and potentially neutrinos emerge. The LHAASO team found that this kind of photomeson process in the innermost relativistic jet naturally reproduces both the unusual energy spectrum and the orbital behavior if protons are accelerated to tens of peta-electron volts. The orbital modulation becomes particularly interesting in this picture. The Wolf-Rayet star is not simply supplying a uniform bath of photons, extending identically in every direction. The geometry changes as the compact object travels around its orbit. The angle between the jet particles, the companion star, the target radiation, and Earth changes. The density of target photons encountered along particular paths changes. Gamma ray absorption can change with orbital phase as well. So the 4.8-hour rhythm is not an unrelated detail sitting on top of the PeV signal. It may be telling researchers exactly where the particle interactions are occurring. The binary system has effectively placed a clock on its own accelerator. Every few hours the geometry repeats. If the gamma rays rise and fall with that same period, the emitting region is unlikely to be a distant cloud that happens to lie in the same direction. It is responding to the orbital arrangement of the stars themselves. That is one reason the result is so different from earlier PeVatron detections. Direction tells you where an event appears on the sky. Variability tells you something about its size. Periodicity can connect it to a particular physical mechanism. Combine all three, and the list of possible explanations becomes much shorter. The energy spectrum adds another unusual feature. Most astrophysical gamma-ray sources become progressively weaker toward their highest energies. That is not surprising. The highest energy particles are difficult to produce, so spectra commonly steepen or cut off. Cygnus X3 behaves strangely. LHAASO measured an unusually hard ultra-high energy spectrum with a photon index around 2.18. After accounting for absorption of PeV gamma rays as they travel through galactic radiation fields, the intrinsic spectral energy distribution appears to rise toward approximately 1 peta-electron volt, with possible hardening above that point. The collaboration describes Cygnus X3 as the hardest UHE source detected by LHAASO in that analysis. The absorption correction matters because PV gamma rays do not travel through the galaxy without interactions. At these energies, a gamma ray can collide with a low-energy background photon and create an electron-positron pair. For Cygnus X3, the cosmic microwave background becomes an important absorber in the peta-electron volt regime. Some of the photons emitted by the source therefore never reach Earth. Researchers calculate how much absorption should occur over the roughly 9 kiloparsec distance used in the LHAASO analysis and reconstruct what the emitted spectrum probably looked like before the journey. The correction is strongest around a few peta-electron volts, reaching a factor of roughly 3 in parts of the spectrum. So the source is actually more extreme than the raw photons reaching LHAASO initially suggest. Nature launched more peta-electron volt gamma radiation than we receive. The Milky Way removed some of it along the way. There is also an intriguing historical detail. Cygnus X3 is not new to claims of extraordinary gamma radiation. During the late 1970s and 1980s, several experiments reported TV and even PeV signals apparently associated with Cygnus X3, sometimes showing its 4.8-hour orbital period. Those claims generated enormous interest because they implied particle acceleration far beyond what astronomers could comfortably explain at the time. Later analyses and more sensitive experiments failed to reproduce the signals consistently, and the early PV claims became controversial. The modern LHAASO paper explicitly notes that history and cautions that the old observations remain uncertain. That makes the current detection especially interesting. It would be tempting to say that LHAASO simply proved that the experiments of the 1980s were correct. That would go too far. The historical measurements were made with very different instruments, and their interpretation remains disputed. What LHAASO has established is that the basic idea once considered so difficult to believe is physically real. Cygnus X3 can produce variable gamma radiation extending into the PeVa regime. The reason earlier experiments may have struggled also becomes easier to appreciate once variability enters the picture. Imagine observing Cygnus X3 during a quiet period. LHAASO's own data show that its UHE signal can fall dramatically between active and quiet states. An experiment operating during the wrong months could reasonably detect nothing. Another instrument observing during an active episode might record a signal. That does not retroactively validate every historical detection, but it shows why a genuinely variable source could produce decades of confusing observational history. This also explains why LHAASO is so well suited to finding it. An instrument that targets Cygnus X3 for 10 hours and then moves on might miss the high state. LHAASO repeatedly scans the same region as Earth rotates and accumulates data year after year. The Cygnus X3 analysis used observations collected from December 2019 through July 2024. That long baseline allowed researchers to separate active periods from quiet ones and compare the PeVa emission with Fermi's GeV light curve. The PeV sky is no longer just becoming a map of sources, it is becoming a movie. That is a substantial change for ultra-high energy astronomy. Once time enters the measurement, researchers can distinguish between a giant diffuse accelerator and a compact engine. They can compare gamma-ray flares with radioactivity. They can compare them with X-ray states. They can search for orbital modulation. Eventually, they can search for neutrinos arriving during the same active periods. That last possibility may become especially important for Cygnus X3. If protons are genuinely undergoing photomeson interactions, charged pions should accompany the neutral pions responsible for gamma-ray production. Charged pion decay produces neutrinos. A neutrino detected from Cygnus X3 during one of its peta-electron volt gamma-ray high states would provide an additional line of evidence for hadronic acceleration. Unlike gamma rays, neutrinos can escape extremely dense environments with little interaction. They also travel without being deflected by magnetic fields. A combined gamma-ray and neutrino detection could therefore reveal both the accelerator and the particle interactions occurring inside it. This is why LHAASO describes Cygnus X3 as an important target for future multi-messenger astronomy. The system also belongs to a larger trend. Cygnus X3 is not the only compact binary forcing its way into the cosmic ray discussion. LHAASO has systematically detected ultra-high energy gamma-ray emission associated with several microquasars containing accreting black holes. In one survey, 5 of 12 suitable galactic systems visible to the observatory showed UHE emission, SS433, V4641, SGR, GRS1915+105, Maxi J182, O+07, O, and Cygnus X1. That was unexpected. For decades, microquasars were studied mainly because they offered nearby laboratories for accretion and relativistic jets. A stellar mass black hole could accrete matter from a companion and launch jets using processes related to those operating around supermassive black holes and quasars. The scale was smaller. The physics happened faster. Astronomers could watch jets appear and change over humanly useful timescales. Now it appears that those jets may also contribute to the galactic cosmic ray population. SS433 provides one of the clearest examples. LHAASO detected extended ultra-high energy emission associated with the central region of the system, overlapping a giant gas cloud. That spatial coincidence supports a hadronic scenario in which particles accelerated by the black hole jet escape and collide with surrounding matter. V4641 SGR produced an elongated UHE gamma-ray structure extending to energies around 800 teravolts. GRS 1915 plus 105, MAX IJ1820+070 in Cygnus X1 were detected with radiation reaching approximately the 100 teravolt range. These systems are not identical. Their companion stars differ, their accretion rates differ, their jet structures differ, their environments differ. Some produce extended gamma-ray emission where cosmic rays have escaped. Cygnus X3 appears to produce at least part of its extreme emission on scales directly connected to the binary. The important common feature is the jet. Material falls toward a compact object, an accretion flow develops. Magnetic fields become twisted and compressed. Part of the available gravitational energy becomes radiation. Part can be diverted into a relativistic outflow. Somewhere within that outflow, particles gain enormous energy. This gives the Milky Way a type of accelerator very different from a supernova shock. A supernova remnant spends an inherited supply of kinetic energy from one explosion. A microquasar is powered by ongoing accretion. As long as matter continues falling onto the compact object, the engine can continue receiving energy. Its activity can turn up and down, the jet can strengthen, it can weaken, it can disappear and return. The resulting cosmic ray injection may therefore be episodic rather than steady. Cygnus X3 makes that behavior visible at peta-electron-volt energies. This could help explain why the galactic cosmic ray spectrum is more complicated than a simple supernova remnant model predicts. LHAASO's recent direct measurements of proton and helium spectra around the knee have revealed evidence for multiple high-energy components rather than one smooth population. The collaboration has specifically pointed to PeVatrons such as microquasars and young massive star clusters as possible contributors to these additional galactic components. That does not mean astronomers can now take the measured cosmic ray spectrum and label one section supernova remnants, another microquasars, and another stellar clusters. Propagation through the Milky Way still mixes everything together. Magnetic fields scramble directions, sources turn on and off, different particle species respond differently, nearby sources can contribute disproportionately. Cosmic rays from an accelerator that was active thousands of years ago may still be wandering through the galaxy today. But LHAASO has supplied something that the field lacked for a long time: actual examples of source classes reaching the required energies. Supernova remnants were plausible from theory and energy budget. Pulsar wind nebula demonstrated extreme electron acceleration. Massive star clusters showed evidence for hadrons reaching tens of peta-electron volts. Black hole jet systems are now joining them. Cygnus X3 goes farther by giving researchers a compact, variable, probably hadronic accelerator whose timing connects the PV emission directly to the binary engine. The title galactic monster is not a scientific classification. Fortunately, astronomy already has enough catalogues, but it describes a useful change in perspective. The objects responsible for the Milky Way's highest energy particles may not be one familiar population operating in one familiar way. They may include exploding stars, dead stars, clusters of young stars, black holes feeding on companions, and jets that accelerate particles inside regions only a few times larger than the Sun. Some accelerators are thousands of years old, some change within months, some fill regions hundreds of light years across, others fit inside a binary orbit lasting 4.8 hours. They reach similar energy ranges through completely different physical routes. And this is where the century-old cosmic ray problem begins to look different from the question Victor Hess unknowingly started asking in 1912. For most of that century, scientists knew energetic particles were arriving, but could not see where they started. Then gamma-ray astronomy began locating extreme accelerators. LHAASO pushed those observations into the petavolt range. Instead of finding one rare machine responsible for everything, it found a growing population. Pulsars, stellar clusters, supernova environments, microquasars. The crab showed that an electron accelerator can operate remarkably close to fundamental limits. Cygnus X3 now shows that a compact binary may push protons beyond 30 peta-electron volts and produce gamma rays several peta-electron volts in energy, while changing its output on measurable timescales. The surprising result is no longer that the Milky Way contains a PeVatron. It is that PeVatron-like behaviour appears in several unrelated kinds of objects. And once 43 ultra-high-energy gamma-ray sources appear in a single LHAASO catalogue, while additional microquasars and new variable systems continue to be identified, the natural question changes again. The challenge is not simply finding out whether our galaxy can build extreme particle accelerators. LHAASO has already shown that it can. The question is how many different kinds it has built, how much each contributes to the cosmic rays around us, and why older models made the highest energy Milky Way look so much quieter than it actually is. The Milky Way has turned out to be a much more powerful particle accelerator than we thought. That is probably the clearest lesson from everything we have seen. For most of the 20th century, the basic problem appeared difficult but manageable. Cosmic rays were arriving at Earth. Most of them were charged particles. Galactic magnetic fields scrambled their directions. Supernova remnants offered a plausible source because their expanding shock waves had enough energy and a known mechanism for accelerating particles. The details were complicated, but the overall picture seemed reasonably organised. Then astronomers began looking above 100 teravolts. The organisation disappeared. LHAASO's first major ultra-high energy observations found 12 gamma-ray sources using only part of the completed detector array and less than a year of data. Those sources produced more than 530 photons above 100 teravolts, including photons extending beyond 1 petavolt. By 2024, LHAASO's first source catalogue contained 90 very high-energy gamma-ray sources, including 43 sources detected in the ultra-high energy band. The number of known UHE gamma-ray sources had increased roughly threefold. 43 sources do not look like one rare accident. They look like a population. That distinction changes the question. If one PeVatron existed in the Milky Way, astronomers could reasonably spend years trying to understand what made that particular object unusual. Perhaps it had an exceptionally strong magnetic field. Perhaps its shock happened to be unusually fast. Perhaps it belonged to some rare class of explosion. Once dozens of ultra-high energy sources appear, rarity stops being a complete explanation. The galaxy is clearly capable of creating extreme particle accelerators through several different routes. Some of those routes begin with pulsars, some involve massive stellar associations, some may involve supernova remnant environments, others involve black holes and neutron stars accreting material from companion stars. And several of these systems appear capable of accelerating particles beyond the energies needed to explain the traditional cosmic ray knee. This does not mean every one of LHAASO's UHE gamma-ray sources is a confirmed proton PeVatron. Gamma rays can be produced by electrons as well as protons, and identifying the underlying particle population remains one of the main challenges of the field. What the catalogue does establish is that extreme particle acceleration is widespread across the Milky Way. LHAASO's own summary notes that pulsar wind nebulae are especially efficient UHE emitters, and that UHE radiation sources are distributed throughout the galaxy. That alone would have been a major revision to the old picture, but the individual sources have made the revision more difficult to ignore. The Crab Nebula showed that a pulsar-powered system can accelerate electrons to PeV energies. The Cygnus star-forming region showed that a huge extended environment containing massive stars can apparently accelerate hadronic cosmic rays to roughly 20 peta-electron volts. LHAASO detected multiple photons above 1 peta-electron volt from the region, including one reaching about 2.5 peta-electron volts, and interpreted the giant gamma-ray bubble as evidence for a continuously operating super-PeVatron. Then, microquasars entered the story. Systems containing accreting compact objects and relativistic jets were no longer merely interesting X-ray binaries. They became possible contributors to the PeV cosmic ray population. LHAASO reported ultra-high-energy gamma rays from several microquasars, including SS433, V4641SGR, GRS1915+105, Maxi J1820+070, and Cygnus X1. In SS433, the gamma-ray emission overlaps a large atomic cloud, supporting a picture in which protons accelerated by the black hole system escape and collide with surrounding matter. V4641SGR produced gamma rays reaching roughly 0.8 peta-electron volts, implying parent particles above 10 peta-electron volts. Cygnus X3 pushed the idea even further. Its peta-electron volt emission varies. It follows the activity of the binary. It shows evidence of the system's 4.8-hour orbital period. The accelerator can therefore be placed extremely close to the compact object, rather than somewhere inside a large unrelated cloud. LHAASO's 2026 result identifies Cygnus X3 as the first variable PeV gamma ray source, and concludes that particles in the system reach at least 30 PeV. That is an astonishing energy for a galactic accelerator. It also creates a useful correction to the title of our journey. We found the fastest thing in the universe. Sounds as though astronomers have discovered a particle moving faster than everything else. They have not. Nothing with mass outruns light in a vacuum. A PeV proton is already travelling extraordinarily close to the speed of light. Give it 10 times more energy, and the difference in its speed becomes almost absurdly small. The remarkable quantity is the energy. These particles are not dramatically faster than every other relativistic particle. They're carrying enormous amounts of energy, while moving at speeds almost indistinguishable from the cosmic speed limit. At those energies, the usual human idea of acceleration becomes misleading. When a car accelerates, we notice because the speed changes substantially. When a proton near the speed of light gains another quadrillion electron volts, most of the change appears in its energy and momentum, rather than as an easily noticeable increase in velocity. So what astronomers have really found is a galaxy filled with some of nature's most extreme particle accelerators. And those accelerators are becoming connected directly with another side of the problem, the particles measured near Earth. LHAASO was designed to study both gamma rays and cosmic rays. That combination is now proving important. Gamma rays can identify locations where extreme acceleration is occurring. Cosmic ray measurements can reveal the energy spectrum and composition of the particles arriving in our neighbourhood. For decades, researchers had these two halves of the story without being able to connect them cleanly. The knee made the difficulty especially obvious. Around a few peta-electron volts, the all-particle cosmic ray spectrum steepens. Was this because the main galactic accelerators reached their maximum energy? Was it because high-energy particles began escaping the Milky Way more efficiently? Did different nuclei cut off at different energies? Was there one dominant source population or several overlapping populations? Those possibilities produced decades of argument because the cosmic ray spectrum alone could not tell researchers which astronomical objects were supplying each component. LHAASO's more recent composition measurements are making the situation more specific. In 2026, the collaboration reported high-precision measurements of the helium spectrum above 0.1 peta-electron volts. Combined with its earlier proton measurements, the data show that hydrogen and helium dominate the knee region, and that both spectra contain unexpected high-energy structures rather than one simple smooth decline. The helium spectrum develops a new component around 1 peta-electron volt and then falls sharply near 7 peta-electron volts. The proton-to-helium balance also changes with energy in a way that is difficult to explain with one universal source population. At lower energies, protons are dominant. Helium becomes more abundant around 0.02 pt-electron volts. Then protons become dominant again near 0.7 pt-electron volts, and remain so to roughly 5 pt-electron volts before helium again becomes more abundant. LHAASO interprets this complicated behavior as evidence that several kinds of galactic accelerators contribute differently at different energies. That is a very different picture from one population of identical supernova remnants, producing one smooth cosmic ray spectrum. Instead, imagine several overlapping populations. One group of sources contributes efficiently at lower energies. Another becomes important as we approach the peta-electron volt range. A rarer population reaches farther. Different source classes may favour different particle compositions. Different galactic environments may also affect how those particles escape and spread. What reaches Earth is then the mixture. You cannot look at one proton arriving over your house and tell whether it began in a supernova shock, a stellar cluster, a micro-quasar jet, or some accelerator that stopped operating thousands of years ago. But the combined energy spectrum carries fingerprints of all of them. The new LHAASO measurements suggest those fingerprints are not smooth. There are bumps, changes in abundance, different cutoffs, additional components. The knee may therefore be less like one accelerator running out of power and more like a changeover between several populations. LHAASO researchers have specifically connected the newly measured PeV components with candidate source classes such as microquasars and young massive star clusters, while noting that the detailed contributions still require further multi-wavelength and multi-messenger study. That qualification matters. Scientific progress does not require pretending every uncertainty has disappeared. The Milky Way is clearly full of extreme accelerators. That part is now observationally difficult to dispute. Exactly how much each source class contributes to the cosmic rays measured near Earth remains less settled. Even the traditional supernova remnant picture is not simply dead. Supernova remnants unquestionably accelerate particles. Some show direct hadronic signatures. Middle-aged remnants may be surrounded by cosmic rays that escaped during an earlier, more energetic period. What LHAASO has made harder to defend is the simplest claim that ordinary young remnants alone explain the entire galactic cosmic ray population up to the knee. As of 2026, LHAASO had not detected gamma rays above 100 teravolts from young supernova remnants, a result significant enough that researchers highlighted it as a major unresolved problem at a dedicated symposium on supernova remnants and galactic cosmic rays. If the old favourite suspects are not routinely reaching the necessary energies, other accelerators have to carry more of the load. Conveniently, LHAASO keeps finding them. This is where the history of cosmic ray research becomes slightly amusing. For a century, researchers were frustrated because the charged particles arriving at Earth would not reveal their sources. Now the problem is almost the reverse. Gamma-ray observatories are identifying so many extreme accelerators that astronomers have to determine which ones matter most. The mystery has not disappeared, it has become more crowded. That is usually a good sign. A field progresses when a question becomes more detailed. What makes cosmic rays was too broad. Which galactic sources accelerate protons through the knee? With what composition? During which stage of their evolution? And how do those particles propagate afterward? Is a much better question. It is also considerably less convenient for anyone hoping to finish early. There are several ways the next stage of this investigation can improve. One is simply more LHAASO data. Ultra-high energy gamma rays are rare. Every additional year increases the exposure. Sources that currently contain only a small number of photons can develop measurable spectra. Faint structures can emerge from the background. Variability can become clearer. Orbital patterns can be tested more strongly. A source that currently appears point-like may eventually reveal extended emission. LHAASO ASO's wide field of view and continuous survey approach make long-term accumulation particularly valuable. Its first catalogue was based on 933 days of data and already contained 43 UHE sources. The collaboration expects the number of identified VHE and UHE sources to grow as exposure increases. Another route is better observations at other wavelengths. Suppose LHAASO finds an extended beta-electron volt gamma-ray source around a pulsar. X-ray observations can measure energetic electrons close to the neutron star. Radio observations can map the larger nebula. Gas surveys can reveal molecular clouds that might be targets for protons. Infrared observations can measure radiation fields important for inverse Compton scattering. Put those together and some models stop working. A purely electron explanation might require more X-rays than are observed. A proton model might require more target gas than actually exists. The most successful interpretation has to survive every wavelength, not just the gamma-ray data. Neutrinos provide another possibility. If PeVatrons collide with matter or radiation and produce charged pions, neutrinos should accompany the gamma-ray producing processes. Unlike cosmic rays, neutrinos are electrically neutral. Unlike gamma rays, they can escape extremely dense environments without being absorbed easily. A neutrino detected from the same direction, and during the same activity period as an ultra-high energy gamma ray source, would therefore be powerful evidence for hadronic acceleration. Cygnus X3 is particularly attractive for this kind of test, because its variable petavolt gamma ray emission provides defined time windows in which neutrino searches can be concentrated. LHAASO itself has identified the system as an important target for future multi-messenger observations. There is also the matter of time. The Cygnus X3 result has opened what LHAASO describes as ultra-high energy time domain astronomy. That phrase represents an important shift. For years, the highest energy gamma-ray sky was treated mainly as a map. Find a source, measure its position, measure its spectrum, accumulate more photons. Now researchers can begin asking when the photons arrive. Does a source flare? Does its petavolt emission follow its X-ray state? Does it brighten when its radio jet turns on? Does it follow an orbital period? Does the maximum gamma-ray energy change during a flare? Time provides another dimension for identifying the accelerator. A giant molecular cloud cannot vary on a 4-hour timescale as one coordinated object. A compact binary can. A pulsar can pulse. A jet can flare. A stellar cluster should look comparatively steady. Timing therefore helps distinguish source classes even when several occupy the same part of the sky. This will be especially useful in regions such as Cygnus, where almost every square degree seems to contain another object capable of causing trouble. There is still a larger question behind all of this. Why is the Milky Way so good at accelerating particles? The ingredients themselves are not mysterious. Gravity releases energy when matter falls toward compact objects. Rotating neutron stars store enormous rotational energy. Massive stars produce powerful winds. Supernovae launch high-speed shocks. Magnetic fields guide charged particles. Turbulence scatters them. Jets move plasma at relativistic speeds. None of those processes is new. What LHAASO has revealed is how often combinations of those ingredients reach extreme conditions. The galaxy does not appear to possess one special accelerator. It possesses an ecosystem of accelerators. A massive star can contribute before it dies through its wind. The cluster in which it formed may accelerate particles collectively. The star can explode and create a supernova shock. Its core can become a pulsar and power a pulsar wind nebula. If the remnant instead becomes part of a binary compact object system, accretion may later power a jet. The same broad stellar population can therefore generate high-energy particles at several different stages. That may be why trying to assign the entire galactic cosmic ray spectrum to one object class has proved so difficult. The galaxy is not required to be that tidy. It can use several machines. It can run them at different times. It can accelerate different particle species to different limits. Then it can mix the particles together through thousands of years of propagation before sending a tiny fraction of them toward Earth. Victor Hess could not have known any of this when his balloon rose above the clouds in 1912. His instrument simply told him that the radiation increased with altitude. Something was coming from above. That was enough to begin the mystery. More than a century later, we know that many of those incoming particles are protons and atomic nuclei. We know their spectrum stretches across an enormous range of energies. We know the knee marks an important transition near the peta-electron volt scale. We know galactic magnetic fields hide the directions of their sources. And now, by following gamma rays instead of the cosmic rays themselves, we can identify places where nature is accelerating particles to precisely the energies that once seemed so difficult to explain. The answer has not turned out to be one source. It is a galaxy full of them. LHAASO's first catalogue alone contained 43 ultra-high energy gamma-ray sources, and later results have added specific examples that expand the list of viable accelerator classes. The Cygnus star-forming region reaches toward 20 peta-electron volt cosmic ray energies. Cygnus X3 reaches at least 30 peta-electron volts, according to LHAASO's 2026 analysis. Pulsar wind nebulae produce peta-electron volt electrons. Micro-quasar jets accelerate hadrons. Supernova remnants remain important but no longer have the field to themselves. And LHAASO's direct proton and helium measurements suggest that several source populations really are leaving separate structures in the cosmic ray spectrum we detect locally. That brings us back to the night sky. If you're still awake, you can look upward and see almost none of this. The Milky Way, where it is visible, appears as a faint band. A bright star may seem completely still. Perhaps an aircraft crosses the view. Maybe a satellite drifts slowly overhead. Nothing looks particularly violent. Yet particles are moving through that same sky with energies produced by exploding stars, spinning neutron stars, clustered stellar winds, and black hole jets. Some have been travelling longer than human civilization has existed. They pass through magnetic fields that gradually erase the direction of home. A few collide with gas and produce gamma rays. Those gamma rays cross thousands of light years. They reach Earth's atmosphere. They disappear in particle cascades. And detectors spread across a mountain in Sichuan reconstruct what happened from the debris. That is how we found the accelerators. Not by catching the cosmic ray and following it backward, by finding the light created when another particle revealed where the acceleration had taken place. There is something satisfying about the fact that the solution required an indirect route. Cosmic rays spent more than a century refusing to point home, so astronomers found something that would. The resulting map is still incomplete. Some sources remain unidentified. Some gamma rays are probably produced by electrons rather than protons. The contribution of individual PeVatrons to the cosmic rays near Earth is still being measured. The exact role of supernova remnants remains under debate, and every new source seems capable of adding a complication that nobody specifically ordered. But the main discovery is already clear. The Milky Way is not struggling to reach PeV energies. It is doing it repeatedly, in several kinds of objects, across large parts of the galaxy, at energies that make our most powerful human accelerators look very small indeed. So if you remember one thing from this journey, it need not be the exact energy of a photon from Cygnus X3 or the number of detectors in LHAASO. Remember the change in the question. For most of the last century, scientists asked where the Milky Way could possibly accelerate particles to such extreme energies. Now we know there are many places capable of doing it. The problem is finding out which machines dominate, how they divide the work, and how their particles combine to create the cosmic ray sky surrounding Earth. If you found this long scientific journey useful, relaxing, or simply strange enough to keep you company for a while, you can leave the video a like and subscribe to Science for Sleep. And before you drift off, think once more about whatever is above you right now. A ceiling, perhaps, clouds, city lights, or maybe a clear view of the Milky Way. Beyond all of it, protons are crossing the galaxy at almost the speed of light. Some were accelerated by stars that no longer exist. Some may have been launched by black holes feeding from companions. Others may have escaped huge stellar nurseries or the magnetic winds of dead stars. They do not arrive with names attached. But little by little, the gamma rays are showing us where to look, and the galaxy above us is turning out to be far more energetic than it ever appeared from the ground.